Have you ever been astonished by mega projects that almost seem impossible? Where human ambition knows no bounds and where construction projects introduce unimaginable innovations. In this documentary, we take you inside the most unbelievable mega projects on the planet. From expansive stadiums to massive underwater tunnels, witness the extraordinary engineering and sheer determination that make these projects a reality. Let's talk about the incredible Braa Bridge, which is located in Romania. This bridge, spanning the Danube River, connects the regions of Moldova and Dobroja and is a testament to the innovative engineering solutions. Costing $600 million to construct, this bridge was awarded in 2017 to a consortium led by the Italian construction company Webuild and Japan's IHI Infrastructure Systems. The construction officially began in December 2018 and involved over 1,350 workers, showcasing the massive scale of the operation. One of the most impressive features of the Braa Bridge is its main span, which stretches 1,120 meters. This makes it the second longest suspension bridge in mainland Europe. The bridge's total length is 1,974 meters, and it includes two imposing towers that raise to a height of 192 meters. These towers are not only structural marvels, but also the tallest structures in Romania. The construction process was highly intricate and involved several critical phases. The bridge deck comprised 86 segments, each weighing approximately 260 tons. These segments were fabricated by Fincantieri in Italy and transported to the construction site via barges. Once at the site, a specialized lifting beam was used to hoist the segments into place, a process that required precise coordination and engineering expertise. The bridge's suspension cables are another engineering marvel. Made from over 18,000 steel wires, the total length of these cables stretches 81,000 kilometers, which is enough to circle the Earth twice. These cables weigh a combined 6,775 tons and are crucial for supporting the bridge deck. The installation of these cables involves intricate techniques to ensure their stability and durability. Building the bridge's foundations posed significant challenges due to the region's soft clay soil and medium-high seismic activity. Advanced techniques such as extensive piling and deep well excavations were employed to ensure the stability of the foundations. Piles within a diameter of 1.8 meters were driven to a depth of up to 45 meters to provide a solid base for the towers. The bridge is designed to withstand extreme conditions, including winds up to 270 kilometers per hour and substantial seismic tremors. This resilience is achieved through meticulous engineering and the use of high-quality materials. The bridge's deck is suspended approximately 40 meters above the river, allowing for the passage of medium-sized ships. A significant engineering feat was the installation of the two main suspension cables. These cables were assembled from thousands of individual steel wires, meticulously intertwined to form robust support structures. The process of anchoring these cables to the towers required precision and advanced engineering techniques to ensure their strength and longevity. But how about one of the biggest stadiums in the United Kingdom? The Tottenham Hotspur Stadium was completed in 2019 at a cost of approximately $1.5 million. Transforming the historic White Hart Lane site in North London, the stadium incorporates cutting-edge design and innovative engineering solutions. The construction spanned 4 years and involved a peak workforce of over 3,800 people, working around the clock to meet the demanding schedule. A standout feature of the stadium is its structural steelwork. The east stand Y column supports level 3 of the stand, reducing the number of columns at ground level and allowing for a dramatic overhang of the facade. Above these columns, an additional transfer structure creates column-free spaces, enhancing the dynamic performance of the stand. The south stand tree structures support the massive 17,000-seat single-tier south stand. These structures consist of 8 individual branches meeting at a complex knuckle point, providing a robust support for the stand above the sliding pitch. The north stand features a cantilever that extends 10 meters over the tier below, using box section rakers supported by plan trusses. This design underwent extensive dynamic analysis to ensure the performance under load. The west stand is supported by 21-meter-tall slender steel box columns, creating a spectacular open space below with propped cantilever balconies and escalator platforms suspended from the structure above. One of the stadium's most innovative features is the world's first dividing retractable football pitch. This engineering marvel allows the grass surface to slide under the south stand to reveal an artificial turf beneath, enabling the stadium to host NFL games and other events. The retractable pitch is 105 meters long and 68 meters wide, and its movement is controlled with precision to maintain structural stability. The roof structure is another engineering highlight, featuring a lightweight cable net design with an outer compression ring and an inner tension ring. This design provides an unobstructed view for all spectators and enhances acoustics, creating an electric atmosphere during matches. The project faced several challenges, including integrating the new stadium into the dense urban fabric of North London and managing the complex logistics of such a large-scale construction site. The proximity to residential areas and the need to keep parts of the old White Hart Lane operational during the initial construction phases added to the complexity. Sustainability measures are a significant aspect of the stadium, including a commitment to zero waste to landfill and initiatives to reduce single-use plastics. The construction and operation of the stadium have significantly boosted the local economy, creating thousands of jobs and revitalizing the surrounding area. We have to travel over to France next for an impressive tunnel mega project. The Mont-Cenis Base Tunnel, also known as the Mount Dambon Base Tunnel, is an ambitious and extensive infrastructure project currently under construction. Aimed at enhancing the high-speed rail connection between Lyon, France and Turin, Italy, this tunnel, set to become the longest rail tunnel in the world at 57.5 kilometers, represents a pinnacle of modern engineering and construction. The construction of the Mont-Cenis Base Tunnel involves several advanced engineering techniques and significant logistical challenges. The project is managed by Tunnel Europe in Lyon-Turin and utilizes both conventional drilling and blasting methods, as well as state-of-the-art tunnel boring machines. The construction is divided into various sections, each with its unique geological challenges and engineering solutions. The tunnel's route from Saint-Jean-de-Maurienne in France to Susa in Italy passes through complex geological formations, including heavily fractured and sheared coal-bearing schists near the French portal. These geological conditions necessitate the use of traditional drilling and blasting methods in certain sections, particularly the initial 5 kilometers on the French side. TBMs are employed for the majority of the excavation, designed to handle both hard rock and softer ground conditions. The TBMs used are bi-mode machines capable of cutting through tough rock formations and using the Earth's pressure balance method in areas with sand or gravel. The project employs approximately 8,000 workers at its peak, who work on multiple fronts simultaneously. This massive workforce is engaged in the excavation of twin tunnels and numerous cross passages, which are essentially for safety and maintenance. In total, 164 kilometers of new tunnels are being excavated, including 4 access shafts and 204 cross passages. One of the significant engineering challenges is managing the logistics of such a large-scale project, especially with the limited access points available. For instance, the single access point provided by the Villeroden-Berget access adit constrains the movement of equipment and materials, requiring precise planning and coordination. The tunnel is designed to accommodate passenger trains traveling at speeds up to 135 miles per hour and freight trains at 75 miles per hour. This modal shift is expected to remove over 1 million lorries from the roads annually, resulting in substantial environmental and economic benefits. Construction progress has been substantial, with 13.5 kilometers of tunneling completed. The project employs 7 TBMs sourced from Schwenau, Germany, and they are equipped to work through both hard rock and soft substrates. The excavation process also involves extensive preparatory work, such as site clearance and the construction of new junctions to facilitate the movements of construction traffic without disrupting local communities. In addition to main running tunnels, the project includes the construction of numerous support structures. These include cross passages for safety and ventilation, access shafts, and underground emergency evacuation facilities. The project also features a sophisticated ventilation system to ensure safe and efficient air circulation throughout the tunnel. It's time to travel over to Turkey next for a record-breaking dam mega project. The Usfi Dam stands at 275 meters tall, making it the highest dam located in Turkey and the fifth highest of its kind worldwide. Construction on the Usfi Dam began in 2013 and culminated in 2022, transforming the landscape and significantly boosting Turkey's energy capacity. The dam is designed as a double curvature concrete arch structure. Its crest length extends 490 meters and the maximum crest elevation reaches 715 meters. This immense structure created a reservoir covering 33.63 square kilometers with a total storage capacity of around 2.2 billion cubic meters. Such a massive reservoir required the precise engineering and use of approximately 220 tons of steel for the gates and 3,800 tons of steel for the penstocks. One of the critical components of the Usfi Dam is its power generation capability. The dam houses a 558-megawatt hydroelectric power plant, equipped with 3 vertical axis Francis turbine units, each rated at 186 megawatts. These turbines are designed to operate with a head of 191 meters and discharge of 107 cubic meters per second. The power plant's annual electricity production capacity is approximately 1.9 billion kilowatt hours. The electricity generated is evacuated through a 380 kilovolt switchyard and transmission line integrating it into Turkey's national grid. The construction of the Usfi Dam faced numerous geological challenges due to the complex and fractured formations of the Çorum Valley. Extensive geotechnical studies were conducted to understand the site conditions and plan the construction accordingly. Digital 3D geotechnical models were employed to manage the design and construction phases, providing a real-time data and enabling adjustments as excavation progressed. This innovative approach ensured the stability and safety of the dam structure. In addition to the dam and power plant, the project included the construction of significant ancillary infrastructure. 4 balanced cantilever viaducts were built, including the 644-meter-long Tekeo Viaduct and the 695-meter-long Usfi Viaduct. Moreover, the project involved constructing 110 kilometers of new roads, 45 tunnels, 22 bridges, and 92 culverts, all designed to support the dam's operation and enhance regional connectivity. The construction process required sophisticated equipment and techniques. The dam's height and curvature demanded precise engineering and the use of advanced construction machinery. Tower cranes with varying capacities, including one 12-ton 280 ECH tower crane, 2 10-ton 200 ECH tower cranes, and 4 6-ton 154 ECH tower cranes were utilized to handle the heavy lifting and placement of materials. It's time to talk about a brand new megatall skyscraper that was recently built in Poland. Varso Tower is located in Warsaw, Poland, and stands at 310 meters tall, making it the tallest building in the European Union. The project, developed by HB Reavis and designed by Foster Plus Partners, began construction in 2015 and concluded in 2022. The towering structure is a key component of the Varso Place mixed-use development, which includes Varso 1 and Varso 2 with heights of 81 and 90 meters. The construction of Varso Tower presented numerous engineering challenges, particularly due to its proximity to Warsaw's Central Railway Station. To address the high water table and poor soil conditions, engineers implemented a deep foundation system with piles extending up to 36 meters below ground. These piles are essential for supporting the tower's immense weight and ensuring long-term stability. The tower's superstructure consists of a reinforced concrete core and steel framework. The concrete core, housing the elevators and emergency staircases, provides the primary vertical support. Surrounding this core is a steel framework made up of high-strength steel beams and columns. This hybrid construction approach allows for large open floor plans with minimal internal columns, maximizing the usable office space and providing flexibility in office layouts. The facade of Varso Tower incorporates advanced engineering techniques to enhance energy efficiency. The triple-glazed curtain walls provide excellent thermal insulation and reduce energy consumption. Automated sharing devices integrated into the facade adjust according to the sun's position, optimizing the building's energy performance. The spire of Varso Tower, which adds 80 meters to its height, is a remarkable engineering achievement. Constructed in sections, each weighing up to 250 tons, the spire was assembled using advanced cranes and the expertise of professional climbers. The spire serves as both aesthetic and functional purposes, housing maintenance platforms and supporting antennas. Inside Varso Tower is designed for modern office needs, with 70,000 square meters of premium office space. The office floors feature a clear height of 3 meters, allowing for spacious open-plan layouts that can be easily reconfigured. High-capacity double-deck elevators serve the offices, with each car serving 2 floors simultaneously to reduce waiting times and improve efficiency. The tower also includes a public observation deck on level 53, offering panoramic views of Warsaw, and a rooftop terrace with greenery on level 49, creating the highest garden in the city. The construction process also is emphasizing sustainability and future-proofing. Early in the project, a thorough analysis of potential innovation solutions was conducted, leading to the strategy that positively impacts the building's performance. The sustainability strategy includes measures to reduce water and energy consumption, contributing to the building's certification. But have you ever seen a bridge that links 2 continents? The Bosphorus Bridge, officially known as the 15 July Martyrs Bridge, links Europe and Asia over the Bosphorus Strait in Istanbul, Turkey. Its construction, which took place from 1970 to 73, overcame significant engineering challenges due to the bridge's location and the environmental conditions of the strait. The idea of a permanent bridge across the Bosphorus dates back to antiquity, but it wasn't until the mid-20th century that this vision began to take shape. The design of the bridge was handled by British civil engineers Gilbert Roberts, William Brown, and Michael Parsons. Construction began in February 1970 with a team of 35 engineers and 400 workers. One of the primary engineering challenges was constructing the deep foundations required to support the bridge. These towers are anchored on massive caissons, which are watertight structures made of steel and concrete. The caissons were floated into position on the water and then gradually sunk by adding concrete, ensuring they reached the necessary depth to provide a stable foundation. This method was crucial to counteract the strong currents and seismic activity typical of the Bosphorus Strait. The bridge features a main span of 1,074 meters, making it one of the longest suspension bridges in the world at the time of its completion. The total length of the bridge, including the approach viaducts, is 1,560 meters. The deck, which accommodates 6 lanes of vehicular traffic, is suspended 64 meters above the water to allow for the passage of large maritime vessels. The deck's aerodynamic design minimizes wind resistance and reduces swaying, a critical consideration given the bridge's considerable length and height. The suspension system is composed of 2 main cables, each containing thousands of individual steel wires bound together. These cables are anchored in large concrete blocks on both ends of the strait, distributing the significant tension forces generated by the bridge's weight and the vehicles that cross it. Vertical suspender cables connect the main cables to the bridge deck, supporting and evenly distributing the load. The bridge towers, standing at 165 meters tall, were another significant engineering achievement. Constructing these towers involved precise engineering to ensure they could bear the load of the bridge and withstand environmental forces. The towers were built using steel sections that were fabricated off-site and then assembled on-site, a process that required meticulous planning and execution. Throughout the construction, engineers had to consider the unique environmental conditions of the Bosphorus Strait, including the strong currents and seismic activity. The bridge's design incorporates features to accommodate these conditions, such as flexible joints and specially designed bearings that allow the structure to move slightly, absorbing and dissipating energy from wind and earthquakes. The Bosphorus Bridge opened to traffic on October 30, 1973, coinciding with the 50th anniversary of the founding of the Republic of Turkey. The completion of the bridge was a significant milestone in civil engineering, demonstrating the capabilities of suspension bridge design and construction techniques that continue to influence bridge projects worldwide. Next up, we have to move to Germany for an incredible stadium project called the Allianz Arena. Located in Munich, this project is a modern architectural marvel and one of the most advanced football stadiums in the world. Constructed between 2002 and 2005, it was designed by the Swiss architects Herzog and de Meuron, with structural engineering handled by Arup. The stadium serves as home ground for both Bayern Munich and TSV 1860 Munich, with a seating capacity of 75,000. The construction of the Allianz Arena required extensive planning and innovative engineering solutions. One of the most striking features of the stadium is its exterior, made up of 2,874 diamond-shaped panels. These panels can be illuminated in various colors, allowing the stadium to change its appearance depending on which team is playing or the type of event being hosted. The material is not only lightweight, but also self-cleaning and resistant to adverse weather conditions, making it an ideal choice for the stadium's facade. The structural frame of the Allianz Arena is composed of reinforced concrete for the bowl and stands, while the roof consists of a steel latticework covered by the panels. The design of the roof and its support ensures that all spectators have an unobstructed view of the field. The upper tier of seating is inclined at 34 degrees, which optimizes sightliness and enhances the spectator experience. During the construction phase, approximately 120,000 cubic meters of concrete and 22,000 tons of steel were used. The precision required for the construction of the stadium's roof was particularly notable. Each panel had to be accurately positioned to ensure proper alignment and lighting effects. The panels are pressurized to maintain their shape and structural integrity, providing both thermal insulation and acoustic dampening. One of the key engineering achievements of the Allianz Arena is its lighting system. Originally using conventional fluorescent lighting, the system was upgraded to a fully digital LED setup provided by Philips. This upgrade involved installing over 5,000 meters of network cable and more than 250 LED lights, which significantly improve energy efficiency and reduced maintenance costs. The LED lights are capable of displaying 16 million colors and can create dynamic lighting effects which are controlled via a sophisticated digital platform. The Allianz Arena interior is designed to cater to a wide range of needs, including hospitality, business, and fan services. It features 2,152 seats, 106 VIP boxes, and extensive facilities such as restaurants, bars, shops, and conference rooms. The stadium also houses a large media area, daycare center, and fan shops, making it a multifunctional venue beyond football matches. Additionally, the Allianz Arena boasts Europe's largest underground car park, capable of accommodating nearly 10,000 vehicles. This massive parking facility was a crucial component of the stadium's design, ensuring easy access for the large number of visitors on match days. Let's travel over to Sweden next, where the Varberg Tunnel is located. This project is part of Sweden's West Coast Line expansion, a significant infrastructure project designed to improve rail capacity and safety between Gothenburg and Lund. The tunnel project involves constructing a 3.1-kilometer tunnel beneath the coastal town of Varberg, featuring a combination of a 2.8-kilometer drill and blast rock tunnel and a 300-meter cut and cover tunnel. Construction of the Varberg Tunnel began in December 2019 with an estimated completion date of 2025. The project is being undertaken by the Swedish Transport Administration and involves a budget of approximately $620 million. The detailed design and construction work are being carried out by Implenia, a major player in the construction industry known for its expertise in large-scale tunneling projects. One of the most significant and challenging aspects of the Varberg Tunnel is dealing with the unique geological conditions. The rock in the northern part of the tunnel, primarily chalcanite, poses significant difficulties for drilling. To address these challenges, the construction team employs advanced techniques such as rock bolting for structural support and pressure grounding to manage water ingress. The main tunnel's cross-section measures 75 square meters, while the service tunnel has a cross-section of about 20 meters, with various cross passages connecting the two. The Varberg Tunnel is part of a broader plan to enhance the West Coast Line, which is a vital transit route connecting southern Sweden to Copenhagen and other parts of Europe. The project aims to facilitate the accommodation of more trains, thereby improving overall rail efficiency and reliability. It includes the removal of the existing railway track and the relocation of the freight yard to the north of Varberg, which will help remove the barrier effect in the central area of the city and improve connectivity with the sea. The new Varberg station, located 150 meters north of the current one, is also part of the project. This station will feature submerged platforms and modern amenities such as cafes, shops, and restaurants. The station's design includes a granite stone base with a wave pattern and an upper section made of wood with a wave-shaped ceiling, blending functionality with aesthetic appeal. In addition to the tunnel and the new station, the project involves constructing several bridges, a 1.3-kilometer cutting, and approximately 2.7 kilometers of new track. Notably, the Ilisu Bridge, a key component of the project, is being built to allow the double-deck track to pass beneath it. Maintaining railway operations during construction is crucial, necessitating meticulous planning and coordination to minimize disruptions. The existing railway line continues to function throughout the construction phase, ensuring the rail services remain uninterrupted. Let's investigate the next megaproject called the Ilisu Dam. Located on the Tigris River in southeastern Turkey, the project represents a major engineering and construction feat. This dam is a key component of Turkey's southeastern Anatolia project, which aims to harness the region's water resources for energy production, flood control, and irrigation. Construction of the Ilisu Dam began in 2006 and concluded in 2020. Standing 135 meters tall and stretching 1,820 meters across, the dam is a concrete-faced rock-filled structure. It has an embankment volume of 43.8 million cubic meters and creates a reservoir with a capacity of 10.4 billion cubic meters. This reservoir is essential for the dam's primary purpose of hydroelectric power generation, with an installed capacity of 1,200 megawatts from 6 Francis turbines, each producing 204 megawatts, generating about 3,833 gigawatt-hours of electricity annually. The dam's construction involves significant engineering challenges due to the region's complex geological and hydrological conditions. To manage these challenges, the Tigris River was diverted through 3 large circular diversion tunnels, each with a diameter of 12 meters and lengths ranging from 897 to 1,099 meters. This diversion was critical to keep the construction site dry, allowing for the building of the dam's foundation and ensuring a stable working environment. A key structural component of the Ilisu Dam is its sophisticated spillway system, designed to manage floodwaters efficiently. This system includes a chute and energy dissipation structures, crucial for controlling the flow of water released from the reservoir and protecting downstream areas from potential flooding. Additionally, the power plant, which houses the turbines, features state-of-the-art digital governors, shutoff valves, and ancillary systems to ensure efficient and reliable operation. Throughout its construction, the project encountered financial and logistical challenges. Initially funded by export credit agencies from Germany, Switzerland, and Austria, these backers withdrew in 2009 due to Turkey's inability to meet over 150 international environmental and social standards. Consequently, Turkey secured alternative funding through public and private bank loans, showcasing the government's commitment to completing the project despite international setbacks. The engineering work also included the construction of substantial infrastructure to support the dam. A 250-meter permanent steel girder bridge was built downstream to facilitate the transport of materials and equipment. Moreover, the project required extensive roadworks, including raising and repairing 52 kilometers of bridge to accommodate the construction needs. The powerhouse of the Ilisu Dam is equipped with 6 vertical Francis turbines, each with a capacity of 204 megawatts and 6 generators rated at 223 megavolt amperes. These components are housed in a facility designed to optimize efficiency and safety. The tail race tunnel, approximately 1,100 meters long with a maximum width of 143 meters, directs water safely away from the powerhouse, ensuring smooth operation. One of the significant engineering achievements of the Ilisu Dam is its ability to integrate advanced technology with practical construction methods. The dam's design and execution require a collaborative effort from various engineering and construction firms, employing modern techniques to address the region's unique challenges. But we have to talk about the iconic skyscraper next, located in Sweden. The Turning Torso, located in Malmö, is a residential skyscraper known for its unique twisting design. Designed by Santiago Calatrava, this structure stands 190 meters tall and was completed in 2005. Its construction involved advanced engineering techniques to achieve its distinctive form and ensure stability and functionality. The turning torso is composed of 9 stacked pentagonal segments that rotate 90 degrees from the base to the top. Each segment consists of 5 floors, with a total of 54 stories. The building's core is a reinforced concrete cylinder which acts as the main structural support, housing the elevator shafts and staircases. The core is completed by an external steel exoskeleton that provides additional support and wind resistance. The foundation of the turning torso is particularly noteworthy. The foundation is a cylindrical box 30 meters in diameter and 15 meters deep, resting on solid limestone bedrock 15 meters below the ground. This ensures the building's stability and minimizes the risk of differential settlement. Piles driven into the bedrock provide further support, preventing unacceptable bending or swaying. The construction progress began with the core, which was built using a sliding formwork system. This method involves a form that climbs upwards as each floor is completed, allowing continuous construction without needing to dismantle and reassemble the framework for each level. The walls around the staircase and lifts were poured into forms suspended from the sliding form, ensuring precision and alignment. Once the core was established, the external steel framework was assembled. This exoskeleton is composed of tapered white steel tubes that wrap around the building, connecting to the core at each level. These tubes are also crucial for the building's lateral stability, helping to resist wind forces and reduce vibrations. The steel framework also supports the triangular sections of each floor, which extend out from the core. Each floor is constructed of prefabricated concrete slabs that fit together like pieces of a puzzle, rotating slightly to create an overall twist. These slabs are anchored into the core and the external steel framework, ensuring a cohesive and stable structure. The slabs are prefabricated off-site to ensure precise specifications, reducing construction time and improving quality control. The facade of the turning torso is clad in a curved aluminum panels designed to follow the building's twists. The windows are arranged to lean either inward or outward, maintaining the flow lines of the design and providing residents with unique views. The facade not only contributes to the building's aesthetic appeal, but also enhances its thermal performance and durability. One of the significant challenges during the construction was managing the twisting geometry while maintaining structural integrity. Engineers used advanced computer modeling and simulation techniques to predict and manage the stresses and loads of the building. These models helped ensure that each segment aligned properly and correctly, and that the building's overall stability was maintained throughout the construction process. The Silvertown Tunnel in London, scheduled for completion in 2025, is a twin-bore road tunnel under the River Thames connecting the Greenwich Peninsula to the Royal Docks. This ambitious project employs state-of-the-art tunnel boring machines, each over 82 feet long and weighing approximately 1,350 tons, designed to handle the challenging geological conditions beneath the Thames, including water-bearing gravels and stiff clays. Construction began with the sinking of deep shafts on both sides of the river. These shafts provided the starting points for the TBMs and will eventually house the tunnel portals. The TBMs, named after historical figures, are equipped with rotating cutter heads that excavate soil and rock, which is then transported out of the tunnel via conveyor belts. The TBMs advance at a rate of around 33 feet per day, lining the tunnel with precast concrete segments as they progress. These segments are bolted together to form a watertight lining, ensuring the structural integrity of the tunnel. One of the primary engineering challenges of the Silvertown Tunnel project is maintaining the stability of the tunnel and preventing groundwater filtration. The construction site is located in a densely populated urban area with significant historical and environmental considerations. To mitigate this, extensive geotechnical surveys and advanced 3D modeling techniques were conducted to ensure the tunnel's stability and integrity. The tunnel is designed to accommodate both current and future traffic demands, with each bore containing 2 lanes and provisioning for future expansion. The alignment of the tunnel was meticulously planned to avoid existing underground utilities and infrastructure, requiring detailed geotechnical surveys and advanced 3D modeling techniques. This planning ensures that the tunnel can be integrated seamlessly into existing road networks, minimizing the need for extensive surface work and disruptions. To enhance the safety and efficiency of the construction process, the project utilizes Building Information Modeling technology. BIM allows for the detailed planning and simulation of construction activities, helping to identify potential issues before they arise and streamlining the construction process. This technology also facilitates collaboration between different teams and stakeholders, ensuring that the project remains on schedule and within budget. The Yia Community Dam in New Zealand is a significant project aimed at providing a reliable water supply for the Tasman region. The construction of this earth-filled dam involved complex engineering techniques to address the unique geological and environmental challenges of the site. The dam, standing 174 feet tall and 1,210 feet long, is designed to store approximately 13 billion gallons of water. The construction process began with extensive site preparation, including the excavation of a large foundation trench to ensure a stable base for the dam. This involved removing unsuitable materials and replacing them with engineered fill. The foundation was then treated with a combination of grouting and drainage systems to manage groundwater and prevent seepage. These measures are critical for maintaining the dam's structural integrity and ensuring long-term stability. The dam's core is constructed using impervious clay, which acts as a barrier to prevent water from seeping through the structure. This clay core is flanked by zones of carefully compacted earthfill, providing support and stability. The construction of these zones involved precise layering and compaction techniques to ensure that each layer met the required specifications for density and moisture content. This meticulous process helps to prevent settlements and maintain the dam's structural integrity over time. To enhance the dam's safety, a robust spillway system was designed to handle potential overflow during periods of heavy rainfall. The spillway consists of a concrete chute and energy dissipation structures, which are designed to safely convey excess water downstream without causing erosion or damage to the dam. The design and construction of the spillway required careful planning and execution, taking into account the potential impacts of extreme weather events and climate change. The construction of the Yia Community Dam also included the development of extensive monitoring and control systems. These systems involve the installation of piezometers, inclinometers, and other instrumentation to monitor the dam's performance and detect any potential issues early. This real-time data is crucial for the ongoing management and maintenance of the dam, ensuring that it operates safely and effectively. The NorthConnex Tunnel in Sydney, Australia, completed in 2020, is a critical infrastructure project designed to alleviate traffic congestion and improve connectivity between the M1 Pacific Motorway and the M2 Hills Motorway. This 5.6 twin tunnel project involved several innovative engineering techniques and addressed various challenges posed by the urban environment. The construction of the NorthConnex Tunnel began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These machines were specially designed to excavate through the sandstone and shale prevalent in the region. Each TBM, over 470 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressure at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing the ventilation and safety systems required for a long tunnel. The NorthConnex Tunnel features a state-of-the-art ventilation system, including jet fans and exhaust stacks, designed to maintain air quality and manage smoke in the event of a fire. The ventilation system is controlled by an advanced monitoring system, which adjusts airflow based on real-time conditions within the tunnel. The construction also included the development of large portal structures at the tunnel entrances, designed to integrate with the existing road network. These structures required extensive earthworks and construction of retaining walls and embankments to support the elevated roadways. The portal structures were designed to provide smooth transitions and minimize disruptions to traffic flow. The NorthConnex Tunnel project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces traffic congestion, improving travel times and road safety in Sydney. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges. The Tappan Zee Bridge in New York, officially known as the Governor Mario M. Cuomo Bridge, was completed in 2018. This replacement for the original Tappan Zee Bridge required innovative engineering and construction techniques to span the Hudson River and address the demands of modern traffic. The construction began with the installation of deep foundation piles driven into the riverbed to provide a stable base for the bridge piers. These piles, made of high-strength steel and concrete, were driven to depths of over 300 feet to reach bedrock, ensuring stability and durability. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure stability and longevity of the structure. The bridge's main span, constructed using a cable-stayed design, features two 419-foot towers and support the bridge deck with 192 cables. The cable-stayed design allows for longer spans and fewer piers in the river, reducing environmental impact and improving navigational clearance for river traffic. The construction of the towers involved the use of jump forms, which allowed for continuous concrete pouring and ensured structural integrity. The bridge deck was constructed using precast concrete segments, which were transported to the site and lifted into place using specialized cranes. Each segment was precisely aligned and connected to form a continuous deck. The use of precast segments allowed for high-quality control and reduced on-site construction time. The segments were pre-tensioned with high-strength steel cables to enhance the bridge's load-bearing capacity and ensure long-term stability. One of these significant challenges during construction was managing the river's tidal fluctuations and weather conditions. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for the precise placement of concrete and other materials. The Tappan Zee Bridge also features advanced safety and monitoring systems. The bridge is equipped with sensors that monitor structural health in real time, providing data on load distribution, temperature, and vibrations. This information is used to ensure the bridge's safety and performance, allowing for timely maintenance and repairs. The construction of the Tappan Zee Bridge demonstrates the application of advanced engineering and construction techniques to create a modern, efficient, and resilient infrastructure asset. The bridge significantly improves traffic flow and connectivity in the Hudson Valley region, addressing the challenges of accommodating both road and river traffic in a densely developed area. The Oroville Dam in California, United States, is the tallest dam in the country at 770 feet. Underwent significant reconstruction following the spillway failure in 2017. The reconstruction project, completed in 2019, involved extensive engineering and construction efforts to restore the dam's safety and functionality. The reconstruction focused on the main and emergency spillways, both of which were damaged during the 2017 incident. The project began with the demolition of the damaged sections, followed by the excavation and preparation of the foundation. This involved the removal of unstable materials and the installation of drainage systems to manage groundwater and prevent future erosion. The main spillway was reconstructed using high-strength roller-compacted concrete, a technique that involves placing and compacting layers of concrete using heavy rollers. This method provides a durable and erosion-resistant surface, capable of withstanding high water flows. The RCC was placed in layers, each approximately 12 inches thick, and compacted to achieve the required density and strength. The emergency spillway was reinforced with a new concrete weir and an extensive network of concrete walls and slabs, designed to control water flow and prevent erosion. The construction of these structures required precise formwork and concrete placement techniques, ensuring that the new spillway could handle extreme flood events. One of the significant challenges during the reconstruction was managing the continued operation of the dam and reservoir. This required careful coordination and planning, including the use of temporary spillways and water management systems to ensure the safety of downstream communities. The project also involved extensive monitoring and testing to verify the performance of the new structures and ensure compliance with regulatory standards. The Oroville Dam reconstruction project demonstrates the application of advanced engineering and construction techniques to address critical infrastructure needs. The project restores the dam's safety and functionality, ensuring the reliable management of California's water resources. The successful completion of this complex and challenging project showcases the capabilities of modern civil engineering to solve significant infrastructure challenges. The new Manila International Airport in the Philippines is an ambitious project designed to alleviate congestion at the existing Ninoy Aquino International Airport. Scheduled for completion in phases with full completion expected by 2025, this airport will feature 4 parallel runways and a capacity to handle 100 million passengers annually. The construction involves massive earthworks, advanced engineering techniques, and meticulous planning to create a state-of-the-art facility. The initial stages of construction focused on land reclamation and site preparation, as the airport is being built on a low-lying area prone to flooding. To address this, engineers employed a combination of dredging and soil stabilization techniques. Millions of cubic meters of sand and fill material were dredged from nearby areas and transported to the site, raising the ground level and creating a stable foundation for the airport infrastructure. The use of geotextiles and ground improvement techniques, such as dynamic compaction and prefabricated vertical drains, helped to accelerate the consolidation of the reclaimed land and improve its load-bearing capacity. The construction of the airport's runways involved precise grading and paving techniques to ensure smooth and durable surfaces. Each runway is designed to accommodate the largest commercial aircraft, requiring layers of high-strength asphalt and concrete. The paving process utilized advanced machinery and techniques, including slip-form pavers and laser-guided screeds, to achieve the required surface smoothness and thickness. The terminal buildings, designed to handle the high-pressure volume, incorporate modern architectural and engineering principles. The construction of these structures involves the use of prefabricated steel components and modular construction techniques, which allow for rapid assembly and high-quality finishes. The terminal roofs are supported by a network of steel trusses, creating large open spaces that enhance passenger comfort and flow. One of the significant challenges of the new Manila International Airport is integrating advanced technological systems. The airport will feature state-of-the-art air traffic control systems, automated baggage handling, and advanced security screening technologies. The installation and integration of these systems require careful coordination between different contractors and suppliers, ensuring that all components work seamlessly together to provide a safe and efficient airport operation. The Red Line Doha Tunnel in Qatar is a key component of the Doha Metro network, designed to provide efficient and reliable public transportation. The construction of this 25-mile-long tunnel, completed in 2019, involved several engineering and logistical challenges, particularly given the region's geological conditions. The tunnel was constructed using tunnel boring machines, which are highly specialized for excavating through the soft rock and soil conditions prevalent in Doha. Each TBM was over 328 feet long and weighed approximately 1,200 tons. These machines were equipped with rotating cutter heads that excavated the soil and rock, which was then transported out of the tunnel using conveyor belts. The construction also involved the careful monitoring and management of ground settlement, particularly in urban areas. Advanced geotechnical instruments such as inclinometers and extensometers were installed to monitor ground movements and ensure the tunnel's stability. This real-time data allowed engineers to adjust construction methods and implement corrective measures as needed, minimizing the impact on existing buildings and infrastructure. The Red Line Doha Tunnel features a dual-track system, allowing for high-frequency train services. The tunnel is equipped with state-of-the-art systems for ventilation, lighting, and emergency evacuation. The ventilation system is designed to maintain air quality and manage smoke in the event of a fire, ensuring passenger safety. The construction process also included the development of underground stations, which required extensive excavation and support systems. These stations were designed with large open spaces to accommodate passenger flow and provide a comfortable environment. The use of advanced structural engineering techniques, such as diaphragm walls and deep foundation piles, ensured the stability and durability of these underground structures. The Red Line Doha Tunnel project showcases the application of advanced tunneling technology and engineering practices to create a modern, efficient, and resilient public transportation system. The project addresses the growing demand for sustainable transportation solutions in Doha, providing a reliable and high-capacity metro network that supports the city's development and connectivity. The DigIndy tunnel system in Indianapolis, United States, is an extensive network of deep rock tunnels designed to reduce sewer overflows into local waterways. Scheduled for completion in 2025, this project involves the construction of over 28 miles of tunnels, each approximately 18 feet in diameter and located 250 feet below ground. The construction process began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These TBMs were specially designed to excavate through the limestone bedrock prevalent in the region. The TBMs, each over 300 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressures at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing groundwater infiltration. The tunnels were designed with a comprehensive dewatering system, including pumps and drainage galleries to control groundwater levels and prevent flooding. Additionally, the tunnel lining included waterproof gaskets and grout injection systems to seal any potential leaks. The DigIndy tunnel system also involved the construction of a large storage and conveyance structures designed to hold and transport combined sewer overflows during heavy rainfall events. These structures were integrated with the existing sewer network, requiring extensive coordination and planning. The project included the installation of advanced control systems, allowing for real-time monitoring and management of these sewer flows. The DigIndy Tunnel System project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces sewer overflows, improving water quality and public health in Indianapolis. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges. The Great Plains Power Station in Canada, located in Moose Jaw, Saskatchewan, is a natural gas-fired power plant designed to provide reliable and efficient energy supplies. Scheduled for completion in 2024, the project involves the construction of a 350-megawatt combined cycle power plant, utilizing advanced gas turbine technology. The construction process began with site preparation and grading, creating a stable foundation for the power plant infrastructure. This involved extensive earthworks, including excavation and compaction, to ensure that the site could support the heavy equipment and structures. The foundations for the gas turbines and other critical components were constructed using reinforced concrete, designed to withstand dynamic loads and provide long-term stability. One of the primary engineering challenges was the installation of the gas turbines and heat recovery steam generators. The gas turbines, manufactured by Siemens, are among the most efficient in the world, capable of converting natural gas into electricity with high efficiency and low emissions. The installation of these turbines required precision alignment and balancing, ensuring optimal performance and reliability. The HRSGs, which capture waste heat from the gas turbines to generate additional electricity, were assembled on-site using prefabricated components, minimizing the construction time and ensuring high-quality fabrication. The power plant's design incorporates advanced cooling systems, including air-cooled condensers, which reduce water consumption and environmental impact. These condensers, constructed using modular components, were installed using large cranes and specialized lifting equipment. The use of air-cooled technology is particularly important in regions with limited water resources, ensuring that the power plant operates sustainably. The Braa Bridge in Gothenburg, Sweden, a vertical lift bridge, is a remarkable engineering project aimed at replacing the aging Doha Bridge. Scheduled for completion in 2021, the Braa Bridge stands out for its innovative design and construction techniques. The bridge spans approximately 1,300 feet and features a vertical lift mechanism, allowing it to accommodate both road and maritime traffic efficiently. The construction began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and passing ships. This foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span is constructed using steel box girders, which are prefabricated off-site and transported to the construction site. These girders were then lifted into place using heavy lift cranes and connected to the piers. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the Braa Bridge is its vertical lift mechanism, which allows the central span to be raised to a height of 150 feet, providing clearance for maritime traffic. The lifting system consists of counterweights and powerful electric motors, designed to operate smoothly and reliably. The bridge's control system includes advanced sensor and automation technology, allowing for precise and efficient operation. The construction also included the development of approach ramps and road connections, integrating the bridge into Gothenburg's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow. The Leonard P. Zakim Bunker Hill Memorial Bridge in Boston, completed in 2003, is a notable example of modern engineering and construction. The cable-stayed bridge, part of the Big Dig project, required innovative techniques and precise execution. The bridge features two inverted Y-shaped towers, each 295 feet tall, constructed using reinforced concrete. The climbing formwork system used for these towers allowed continuous concrete pouring, ensuring structural integrity and minimizing construction time. The main span of the bridge, stretching 745 feet, is supported by 116 high-strength steel cables, arrived in a harp configuration. These cables were meticulously tensioned to ensure even load distribution. Each cable was anchored at the bridge deck and tower, requiring precise calculations to maintain balance and stability. The deck itself was constructed using precast concrete segments, which were transported to the site and assembled using a launch gantry, minimizing disruptions and expediting the construction process. Maintaining traffic flow on the existing I-93 highway while building the new bridge was a significant challenge. This required a series of temporary supports and careful staging of construction activities. Additionally, the bridge had to be integrated within the city's underground Central Artery Tunnel, necessitating complex coordination between different construction teams. Extensive geotechnical engineering ensured the stability of the bridge foundations, which were anchored in deep bedrock to withstand the weight and dynamic loads of the structure. The Zakim Bridge's design incorporated seismic considerations. Given Boston's susceptibility to earthquakes, engineers used advanced modeling to simulate seismic events and ensure the bridge's resilience. The towers and deck were designed to move independently,
allowing them to absorb and dissipate energy during an earthquake, minimizing structural damage. One of the issues faced during construction was soil stability and water infiltration, which required additional measures such as dewatering and ground improvement techniques. However, these challenges were overcome through innovative engineering solutions and meticulous planning. The bridge's design also includes provisions for thermal expansion and contraction, with expansion joints made of flexible materials to allow the bridge to expand and contract with changes in temperature without compromising structural integrity. The Captain Cook Bridge in Brisbane, Australia, completed in 1972, is a significant construction project that spans the Brisbane River, connecting the southern suburbs to the central business district. The bridge's construction involved several innovative engineering techniques and addressed various challenges posed by the river's width and tidal fluctuations. The bridge is a pre-stressed concrete structure consisting of a continuous box girder design. The construction process began with the sinking of deep caissons into the riverbed to provide stable foundations for the bridge piers. These caissons, large cylindrical structures, were constructed using reinforced concrete and driven into the riverbed using pile drive equipment. Once in place, they were filled with concrete to create solid footings for the bridge. The box girder sections were precast in segments on shore and then transported to the construction site using barges. These segments were assembled using the balanced cantilever method, where sections were added symmetrically on either side of the piers. This method ensured that the structure remained balanced and stable throughout the construction process. Each segment was lifted into place using specialized cranes and temporarily supported until the adjacent segments were connected and the concrete joints cured. One of the significant challenges during construction was managing the tidal fluctuations and river traffic. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for precise placements of concrete and other materials. The bridge's design also included provisions for seismic activities and thermal expansion. Expansion joints were incorporated into the structure to accommodate temperature variations and prevent cracking. These joints, made of flexible materials, allowed the bridge to expand and contract with changes in temperature without compromising structural integrity. The New Challange Bridge in Sri Lanka, completed in 2020, is a significant infrastructure project aimed at improving connectivity between Colombo and its suburbs. This 6-lane bridge spans the Challange River and incorporates several innovative construction techniques to address the challenges posed by the river's width and tidal variations. The construction process began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and river currents. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span, constructed using a steel box girder design, involved the prefabrication of large segments off-site. These segments were transported to the construction site using barges and lifted into place using heavy lift cranes. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the New Challange Bridge is its cable-stayed design, with cables arranged in a fan configuration. These cables, made of high-strength steel, support the main span and provide additional stability. The cable-stayed design allows for a longer span and reduces the number of piers needed in the river, minimizing environmental impact and improving navigation clearance for river traffic. The construction also included the development of approach ramps and road connections, integrating the bridge into Colombo's existing transportation network.
This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow.
Berlin Central Station in Germany is one of Europe's largest and most modern railway stations, serving as a major transportation hub in the heart of Berlin. The station's construction involves significant engineering and architectural challenges, including the integration of multiple rail lines and the creation of a multi-level structure to accommodate high-speed, regional, and local train services. The station's design features a vast glass roof and an extensive use of steel and concrete to create a spacious and open interior. The construction process for Berlin Central Station began with the excavation of a large underground cavity to house the lower levels of the station. This was followed by the installation of reinforced concrete foundations and structural supports to create the station's framework. The use of advanced construction techniques, such as top-down construction, allowed for the simultaneous construction of the upper and lower levels, reducing overall construction time. In this method, the ground-level structure is built first, followed by the excavation and construction of the lower levels. This technique minimizes the need for extensive temporary supports and allows for faster progress. The station's glass roof was assembled using prefabricated steel and glass components, which were lifted into place using large cranes and carefully aligned to ensure structural integrity and aesthetic appeal. The roof's design allows natural light to flood the interior, creating a bright and welcoming environment for passengers. The extensive use of glass also provides panoramic views of the surrounding cityscape. The construction of Berlin Central Station also involved the installation of complex rail systems. This included laying new tracks, installing signaling systems, and integrating with the existing rail network. High-precision track laying machines were used to ensure the tracks were positioned with millimeter accuracy, essential for the smooth operation of high-speed trains. The Ningbo-Zhoushan Port expansion in China is a massive infrastructure project aimed at enhancing the capacity and efficiency of one of the world's busiest ports. The expansion includes the construction of new deep-water berths, container terminals, and logistics facilities to accommodate the growing volume of international trade. One of the primary challenges is the dredging and land reclamation required to create the new berths and terminals. Advanced dredging techniques and equipment are employed to ensure precision and minimize environmental impact. The project also involves the construction of state-of-the-art port infrastructure, including automated container handling systems, advanced logistics facilities, and modern navigation aids. To improve connectivity, extensive road and rail networks are being developed to link the port with major industrial and commercial centers. The expansion also incorporates sustainable practices, such as energy-efficient systems and renewable energy sources, to reduce the port's environmental footprint. Once completed, the Ningbo-Zhoushan Port expansion will enhance China's position as a global trade hub, boosting economic growth and facilitating international commerce. The project is expected to significantly increase the port's capacity, allowing it to handle larger vessels and more cargo efficiently. The expansion will also create job opportunities and stimulate economic development in the surrounding regions, contributing to China's overall economic growth. The construction process utilizes advanced port machinery such as automated stacking cranes, high-capacity dredgers, and specialized container handling equipment to ensure efficient and precise development of the new port facilities. It's time to investigate the London Array offshore wind farm next. This colossal project, operational since 2013, spans an area of 100 square kilometers, roughly the size of 14 football fields, making it one of the largest offshore wind farms in the world. Comprising 175 turbines, each towering up to 147 meters high, the London Array has a peak capacity of 630 megawatts. This enormous output is capable of powering nearly 500,000 homes, significantly contributing to the UK's renewable energy targets. The installation of turbines in a marine environment posed complex challenges, from logistical hurdles in transporting massive components by sea to installing them on the seabed amidst varying weather conditions. The project also necessitated the laying of over 200 kilometers of underwater cables that connect the turbines to each other and to the power grid onshore. Safety and environmental sustainability were paramount throughout the construction phase. Innovative measures were implemented to protect the local marine ecosystem, including the use of bubble curtains, a technique that minimizes the impact of underwater noise on marine life during pile driving activities. The scale of the London array can be likened to that of the Hoover Dam in terms of electricity output, although the technologies and the environments they harness are vastly different. The investment of $2.35 billion into this project places it among the titans of European mega-projects. Sardar Sarovar Dam in India is one of the largest and most complex dam projects in the country. Located on the Narmada River in Gujarat, the dam stands at a height of 535 feet and creates a reservoir with a capacity of 7.7 million acre-feet. The construction of Sardar Sarovar Dam involves several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Sardar Sarovar Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,450 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines. The Hefei-Wuhan High-Speed Railway in China is a major infrastructure project aimed at enhancing connectivity between the cities of Hefei and Wuhan. This 300-mile high-speed rail line is designed to support train speeds of up to 220 miles per hour, reducing travel time between the two cities to just over 1 hour. The project involves the construction of multiple tunnels, bridges, and viaducts to navigate the complex terrain. One of the key engineering challenges is the construction of the long tunnels through mountainous regions, which requires advanced tunnel boring machines and precise engineering techniques. The railway line is equipped with state-of-the-art signaling and communication systems to ensure safety and efficiency. To minimize environmental impact, extensive environmental assessments and mitigation measures are implemented, including wildlife crossings and noise barriers. The project also includes the construction of modern stations equipped with advanced passenger amenities and accessibility features. The Hefei-Wuhan High-Speed Railway is part of China's broader efforts to expand its high-speed rail network, promoting economic development and regional integration. Once completed, the railway line will provide a fast, efficient, and environmentally friendly transportation option, boosting connectivity and economic growth in the region. The project is expected to significantly reduce carbon emissions by providing a greener alternative to air and road travel. The Hefei-Wuhan High-Speed Railway will not only improve travel efficiency, but also stimulate economic activities in the regions it connects, fostering greater regional cooperation and development. The railway is also expected to enhance tourism by making it easier for travelers to access the cultural and historical attractions in both cities, further contributing to the local economies. The construction of the railway employs high-speed rail technology, including the use of continuous welded rail, slab track systems, and automated track-laying machines to ensure smooth and reliable train operations. Let's travel to the United Kingdom next for the Hinkley Point C power station. This project, which broke ground in 2016, aims to provide a secure, low-carbon energy source capable of powering approximately 6 million homes. The Hinkley Point C project is the first new nuclear power station to be built in the UK in over 20 years. Upon completion, it will house 2 European pressurized reactors, each expected to deliver 1,630 megawatts of power. The significance of this development extends beyond energy generation. It's a critical move towards sustainable industrial growth and job creation. The construction of Hinkley Point C has brought together a workforce of around 25,000 over its lifespan. The project site spans 430 acres, and the volume of concrete to be used in the construction is projected to be enough to fill 75 football stadiums. Technologically, Hinkley Point C employs advanced safety and operational features, including a robust cooling system and state-of-the-art security measures to ensure safe, continuous operation. The design also incorporates lessons learned from previous nuclear developments, making it one of the safest and most efficient nuclear power plants globally. Challenges faced during the project have been substantial. These include regulatory hurdles, financial negotiations, and public opposition based on safety concerns. Moreover, the project's timeline has been impacted by the intricate nature of nuclear construction and the need for rigorous inspection and quality control to meet stringent nuclear safety standards. Economically, the investment in Hinkley Point C is significant, with costs estimated at around $43 billion. This makes it one of the most expensive energy projects ever undertaken, comparable in cost to the creation of vast urban developments. Hinkley Point C's strategic importance is underscored by its projected output, which will provide about 7% of the UK's total electricity needs with reliable, low-carbon energy. This is crucial for a country aiming to phase out coal by 2024 and reduce greenhouse gas emissions significantly by 2050. The Great Man-Made River Project in Libya is one of the largest and most ambitious water supply projects in the world. The project involves the construction of a vast network of underground pipelines and reservoirs to transport water from aquifers deep in the Sahara Desert to the coastal cities of Libya. The construction of the Great Man-Made River Project involves several significant engineering challenges, including working in a remote and arid environment with limited infrastructure. The construction process begins with extensive surveying and land acquisition to establish the route of the pipelines. This is followed by large-scale excavation work, which involves the use of heavy machinery such as bulldozers, excavators, and dump trucks to remove vast quantities of earth and rock. The pipelines are constructed using reinforced concrete and steel, which provide durability and strength. The construction of the pipelines involves the use of advanced welding and coating techniques to ensure the joints are secure and the pipes are protected from corrosion. The pipes are laid in trenches, which are then backfilled with soil to provide additional support and protection. The project also includes the construction of large reservoirs and pumping stations to store and transport the water. The engineering challenges of the Great Man-Made River Project include dealing with harsh environmental conditions, such as extreme temperatures and arid landscapes. Construction crews must work in difficult conditions, often facing temperatures exceeding 120 degrees Fahrenheit. Additionally, the remote location of the project requires the establishment of temporary construction camps and logistical support to provide essential services to the workers. Advanced surveying and mapping technologies are used to plan the pipeline routes and ensure precise alignment and gradient. This ensures that water flows smoothly through the pipelines and reaches the intended areas without excessive energy loss. The use of GPS and drone technology allows engineers to monitor progress and make real-time adjustments to the construction process. The new Everton Stadium, also known as Bramley Moor Dock Stadium, is a landmark development for Everton Football Club in Liverpool, United Kingdom. This 50-20-seat stadium is being constructed on the historic Bramley Moor Dock, a UNESCO World Heritage Site, blending modern architecture with the area's rich industrial heritage. The project involves extensive groundworks to stabilize the dock, including the use of advanced piling techniques and ground improvement methods to ensure a solid foundation. One of the major engineering challenges is preserving the historic dock wall while integrating it into the stadium's design. The construction also includes a complex drainage system to manage water levels and prevent flooding. The stadium features a striking brick facade, echoing Liverpool's historic buildings, and a steep, single-tier home stand to enhance the matchday atmosphere. Inside, the stadium is equipped with state-of-the-art facilities, including hospitality suites, retail spaces, and a museum celebrating the club's history. Advanced construction techniques, such as the use of prefabricated components and modular construction, are employed to ensure efficiency and precision. Sustainability is a key focus, with the project incorporating renewable energy sources, energy-efficient systems, and sustainable materials. The construction also emphasizes the use of local materials and labor, supporting the regional economy. Once completed, the new Everton Stadium will not only provide a world-class venue for football, but also serve as a catalyst for the regeneration of the surrounding area, creating jobs and boosting the local economy. The stadium is set to become an iconic landmark in Liverpool, attracting tourists and sports enthusiasts from around the world. The project also includes community engagement initiatives, ensuring that the new stadium benefits the local population through improved infrastructure and social programs. Additionally, the stadium's design incorporates advanced acoustics and lighting systems, enhancing the overall spectator experience and making it a premier venue for various events beyond football. The construction process utilizes heavy machinery such as pile drivers, concrete mixers, and prefabrication assembly lines to ensure timely and accurate completion of the project. But what about the construction of a gigantic port? The London Gateway Port, strategically positioned on the north bank of the River Thames, is the United Kingdom's premier deep-sea port and Europe's most advanced logistics hub. Opened in 2013, this sprawling facility covers over 1,500 acres, equivalent to more than 1,000 football fields. It boasts 6 deep water berths and has the capacity to handle the world's largest container ships, which can carry up to 18,000 containers each. This capability is crucial in accommodating the ever-increasing size of global shipping vessels and maintaining the UK's competitive edge in international trade. The construction of London Gateway involved over 10,000 workers at peak times, drawing on a range of specialties from marine construction to high-tech automation. The port utilizes some of the most advanced cranes and automated stacking cranes in the world, all designed to minimize cargo handling times and maximize efficiency. One of the significant challenges faced during the construction was maintaining strict environmental regulations. The project included creating a new 1,500-acre wildlife reserve as part of its commitment to biodiversity, which serves as a habitat for birdlife and other species, thereby balancing industrial development with environmental conservation. The economic implications of London Gateway are profound. A special feature of the port is its ability to function as a tidal port, which maximizes accessibility for shipping regardless of tidal movements. This feature is crucial for maintaining constant flow in operation, distinguishing it from other ports that may face operational delays due to tidal constraints. The investment in London Gateway Port of $1.87 billion mirrors the financial commitment seen in projects like the expansion of Barcelona's El Prat Airport, another critical infrastructure aimed at boosting capacity and economic growth. Marina Bay Sands in Singapore is an iconic integrated resort that includes a hotel, casino, convention center, shopping mall, and observation deck. The construction of Marina Bay Sands involves significant engineering challenges and the use of advanced construction techniques. The project began with extensive site preparation, including the reclamation of land from the sea. This involved the construction of a cofferdam to create a dry work area, followed by the installation of deep foundations to support the resort's massive structure. The foundations were constructed using board piles and diaphragm walls, which provide stability and strength. The main structure of Marina Bay Sands consists of 3 interconnected towers, each standing at 55 stories high. The towers are constructed using reinforced concrete and steel frames with a central core providing additional stability. The construction of the towers involved the use of high-strength concrete and advanced formwork systems to ensure precise alignment and smooth finishes. One of the most impressive features of Marina Bay Sands is the Sky Park, a large observation deck that spans the 3 towers. The Sky Park was constructed using prefabricated steel sections, which were lifted into place using large cranes. The sections were then welded together to create a continuous structure, with additional support provided by steel cables. The resort also includes a large convention center, which was constructed using a combination of reinforced concrete and steel frames. The convention center features large open spaces with high ceilings, which were created using long-span steel trusses. The construction of the shopping mall involved the use of glass and steel to create a bright and modern interior, with high-quality finishes and fixtures. The Rome Metro Line C extension is an ambitious project aimed at expanding Rome's metro system to improve connectivity and reduce traffic congestion in the city. The extension adds several new stations and 11 miles of track to the existing line, stretching from central Rome to the suburbs. The project involves complex tunneling operations beneath the historic center of Rome, requiring careful excavation to avoid damaging ancient structures and archaeological sites. Tunnel boring machines equipped with state-of-the-art ground-penetrating radar are used to detect and navigate around sensitive areas. The construction also incorporates advanced engineering techniques, such as the use of precast tunnel segments to accelerate the build process and enhance structural integrity. One of the significant challenges is managing the excavation and removal of spoil in a densely populated urban area. This is addressed through a combination of conveyor systems and specialized transport vehicles to minimize disruption to daily city life. The new stations are designed with modern architectural elements, integrating seamlessly with Rome's historic aesthetics, while providing improved accessibility features like elevators and escalators. The project also includes upgrading the existing stations and infrastructure to accommodate the increased passenger capacity. Advanced safety systems, including fire detection and suppression, as well as real-time passenger information systems, are installed to enhance commuter experience. The extension also incorporates green building standards, ensuring energy-efficient station operations and reduced carbon footprints. Upon completion, the Metro Line C extension will significantly reduce travel times, improve urban mobility, and contribute to the reduction of air pollution by encouraging the use of public transportation. The project is expected to transform the commuting experience in Rome, making it more efficient and reliable, and enhancing the overall quality of life for residents and visitors alike. The extension will also support the city's economic development by improving access to key commercial and cultural districts. It's time to go to Germany next, where Stuttgart 21 is being constructed. This project is a visionary rail and urban development project that fundamentally transforms Stuttgart's transport infrastructure and urban landscape. Initiated with construction in 2010, Stuttgart 21 is one of the most complex rail projects in Europe. It involves the excavation of 57 kilometers of new tunnels and the construction of 25 kilometers of new rail lines. The scale of earth moved in this project is staggering enough to fill several thousand Olympic-sized swimming pools. This involves intricate engineering to handle and dispose of materials while ensuring stability for new and existing structures. Additionally, the project includes the redevelopment of 100 hectares of land in the city center, which will provide space for new homes, parks, and commercial areas once the rail lines are underground. The project has faced numerous challenges since its inception, including public protests and escalating costs. Originally estimated at around $4.5 billion, the budget has since ballooned to approximately $9.8 billion, making it one of the most expensive infrastructure projects in Europe. The increase in costs and the time required to manage such a massive undertaking have been points of contention and public debate. Despite these challenges, the benefits of Stuttgart 21 are projected to be significant. The new station will reduce travel times, increase train capacity, and improve connectivity between Stuttgart and major European cities. It's expected to enhance local and regional economic development and reduce traffic congestion in Stuttgart's city center. Approximately 5,000 workers are involved in this project, employing cutting-edge construction techniques and technologies. For instance, the use of slab track, a type of railway track that provides a consistent and stable base, is a key feature in modernizing the railway system. Comparatively, the total cost of $9.8 billion reflects a financial scale similar to that of constructing the new Terminal 5 at London's Heathrow Airport, underscoring the significant investment required for state-of-the-art infrastructure projects. Pittsburgh International Airport in the United States is undergoing a major modernization project to enhance its capacity and facilities. The project includes the construction of a new terminal, the expansion of existing terminals, and improvements to the airport's runways and taxiways. The construction process involves extensive use of precast concrete and steel structures to ensure rapid and efficient assembly. The new terminal's construction begins with site preparation, which includes clearing and grading the site and installing deep foundations to support the terminal structure. Precast concrete panels and steel beams are then assembled to form the terminal's framework, followed by the installation of roofing and cladding systems. The use of precast concrete allows for high precision in manufacturing, reducing the likelihood of errors during assembly and speeding up the construction process. The expansion of existing terminals involves complex engineering work to integrate new structures with the old ones seamlessly. This requires careful planning and execution to avoid disruptions to airport operations. Advanced construction techniques, such as modular construction and prefabrication, are used to minimize on-site work and reduce construction time. The project also includes significant improvements to the airport's runways and taxiways. This involves the construction of new taxiways and the expansion of existing runways to accommodate larger aircraft. High-precision paving machines are used to ensure the surfaces are smooth and level, which is critical for safe aircraft operations. Additionally, advanced lighting and navigation systems are installed to enhance visibility and safety. The Royal Gorge Bridge in the United States is undergoing a major renovation project to enhance its structural integrity and improve visitor experience. Spanning 1,260 feet across the Arkansas River in Colorado, the bridge is one of the highest suspension bridges in the world, towering 955 feet above the river. The renovation involves replacing the wooden deck with high-strength, weather-resistant materials to ensure durability and safety. Advanced construction techniques, such as the use of prefabricated components and modular assembly, are employed to minimize disruption to visitors and ensure precision. One of the primary challenges is maintaining the structural integrity of the historic bridge while incorporating modern materials and technologies. The project also includes the installation of new safety features, such as reinforced railings and automated monitoring systems to detect structural stresses. The renovation aims to preserve the bridge's historic character while enhancing its functionality and safety. Once completed, the Royal Gorge Bridge will continue to be a major tourist attraction, providing breathtaking views and a unique engineering marvel for visitors to enjoy. The renovation also includes improvements to the surrounding infrastructure, such as upgraded walkways and viewing platforms, enhancing the overall visitor experience. The project is expected to boost the local economy by attracting more tourists and providing new job opportunities in the tourism sector. The Royal Gorge Bridge renovation underscores the importance of preserving historic structures while adapting them to meet modern safety and usability standards. The construction process utilizes specialized machinery such as high-capacity cranes, prefabrication assembly lines, and automated monitoring systems to ensure the structural integrity and longevity of the bridge. Next up, we have to look at a project that's located in between Denmark, Sweden, and Germany. The Kriegers Flak offshore wind farm stands as a towering testament to Europe's commitment to renewable energy. With 72 turbines spinning over an area of 132 square kilometers, this wind farm is a crucial step toward achieving sustainability on a grand scale. The construction of Kriegers Flak began with the dual aims of enhancing energy production and reducing carbon emissions across the region. Upon its completion in 2021, it became one of the largest offshore wind farms in the world, boasting a capacity to generate 600 megawatts of power. This is enough energy to supply approximately 600,000 households annually, significantly impacting the region's energy dependency on fossil fuels. The installation of each turbine at Kriegers Flak was a meticulous process, involving specialized ships capable of handling the enormous weight and size of the components. Each turbine reaches up to 188 meters in height, nearly as tall as the Gherkin in London. A unique feature of Kriegers Flak is its role in supporting biodiversity. Artificial reefs were created using materials from the construction to promote marine life in the Baltic Sea, showcasing an innovative approach to environmental stewardship within an industrial project. Financially, the wind farm represents a significant investment in green technology, with a total cost of $1.4 billion. This investment underscores the economic scale of transitioning to renewable energy sources, comparable in cost to constructing major infrastructure like the new Queensferry crossing in Scotland. Moreover, Kriegers Flak serves as a critical junction for power connectivity in Europe. It includes an innovative feature that allows it to serve as an interconnector between Denmark and Germany, not only generating electricity but also facilitating energy trade between countries, enhancing grid stability and supply security across borders. San Diego International Airport in the United States is undergoing a major expansion to enhance its capacity and facilities. This project includes the construction of a new Terminal 1, which will replace the existing terminal and increase the airport's capacity by 11 million passengers per year. The construction involves extensive use of precast concrete and steel structures to ensure rapid and efficient assembly. One of the significant challenges is maintaining airport operations during construction, which requires detailed phasing plans to minimize disruptions. The new terminal will feature state-of-the-art baggage handling systems, advanced security screening technologies, and improved passenger amenities. The construction process for the new terminal involves several key stages, including site preparation, foundation work, structural assembly, and interior finishing. Site preparation includes clearing and grading the site, followed by the installation of deep foundations to support the terminal structure. Precast concrete panels and steel beams are then assembled to form the terminal's framework, followed by the installation of roofing and cladding systems. The use of precast concrete allows for high precision in manufacturing, reducing the likelihood of errors during assembly and speeding up the construction process. The terminal's advanced baggage handling system involves installing miles of conveyor belts, scanners, and sorting machines. These systems are designed to handle thousands of bags per hour with high accuracy, ensuring that passengers' luggage is efficiently processed and delivered. The security screening area is equipped with the latest technologies, including body scanners, automated lanes, and advanced detection systems to enhance security and reduce waiting times. The construction of the terminal also includes extensive interior work. High-quality finishes, modern lighting, and comfortable seating areas are specified to create a pleasant environment for passengers. Retail and dining areas are designed with flexibility in mind, allowing for easy reconfiguration as needs change. The project also involves significant improvements to the airport's runways and taxiways, including the construction of new taxiways and the expansion of existing runways to accommodate larger aircraft. These enhancements are critical to increasing the airport's capacity and efficiency. The North Offshore Wind Farm in the Netherlands is a major renewable energy project designed to harness the power of the North Sea. This offshore wind farm, consisting of 150 turbines, is set to generate 1.2 gigawatts of electricity, enough to power over 1 million homes. The construction involves the installation of massive wind turbines, each standing over 650 feet tall, mounted on monopile foundations driven deep into the seabed. One of the primary challenges is the harsh marine environment, including strong winds and waves, which necessitate the use of advanced engineering techniques and durable materials. Specialized installation vessels and cranes are used to transport and erect the turbines. The project also includes the construction of an offshore substation and extensive underwater cabling to connect the generated power to the onshore grid. Environmental assessments and mitigation measures are implemented to minimize the impact on marine life and ecosystems. Once completed, the North Offshore Wind Farm will significantly contribute to the Netherlands' renewable energy capacity, reducing carbon emissions and promoting sustainable energy development. The project represents a significant step towards meeting the country's renewable energy targets and reducing dependence on fossil fuels. The wind farm is expected to generate substantial economic benefits, including job creation and increased investments in the local economy. The project also highlights the Netherlands' leadership in renewable energy and offshore wind technology, setting an example for other countries to follow. The construction process employs advanced machinery such as specialized installation vessels, high-capacity cranes, and underwater cable-laying equipment to ensure the precise and efficient assembly of the wind turbines and associated infrastructure. We travel to France next for a gigantic canal megaproject called the Seine-Nord-Europe Canal. Designed to connect the Oise River at Campigny to the Dunkirk-Escaut Canal near Cambrai, this ambitious canal extends over 107 kilometers, providing a high-capacity waterway link between Paris and major northern European ports. Slated for completion in 2028, the canal aims to alleviate road and rail congestion by providing an eco-friendlier option for cargo transport. The canal is expected to support vessels up to 400 tons, double the capacity of most existing barges in the region. This increase not only maximizes cargo volumes, but also drastically reduces the environmental impact per ton of goods transported, aligning with broader European sustainability goals. The construction of the canal involves extensive earthworks, with an estimated 50 million cubic meters of soil to be excavated. This volume of soil is enough to fill the Great Pyramid of Giza approximately 5 times over. Furthermore, the project will include the construction of 3 massive locks, each capable of lifting vessels up to 13 meters high, akin to navigating a 4-story building vertically through water. In addition to the primary waterway, the project includes the creation of 55 structures, including aqueducts and bridges, to maintain the cross-connections between divided regions and to ensure that local ecosystems and communities remain intact. The workforce on this project is tasked not only with the physical construction, but also with implementing advanced hydroengineering techniques to manage the water flow and ensure safety during the canal's operation. One of the most innovative aspects of the Seine-Nord-Europe Canal is its incorporation of smart technology. The canal will feature automated lock systems and remote-operated bridges, enhancing operational efficiency and safety. This technological integration positions the canal as a future-proof infrastructure, ready to handle the anticipated increase in automated and digital shipping processes. With a total cost of $5 billion, the Seine-Nord-Europe Canal is comparable in ambition and budget to other major infrastructure projects like London's Crossrail project. Leathermouth Rail Link in Scotland is a major infrastructure project aimed at reconnecting the Leathermouth area to the national rail network. The project involves the construction of new railway tracks, the renovation of existing infrastructure, and the creation of new stations. The construction process involves several significant engineering challenges, including working in a densely populated urban environment and integrating with existing rail infrastructure. The construction process begins with extensive site preparation, including the clearing and grading of the site and the installation of deep foundations to support the new railway tracks. The tracks are constructed using high-quality steel rails and reinforced concrete sleepers, which provide durability and stability. The construction process also involves the installation of advanced signaling and communication systems to manage train movements and ensure passenger safety. The renovation of existing infrastructure includes the upgrading of bridges, tunnels, and level crossings to accommodate the new railway tracks. This requires careful planning and execution to avoid disruptions to road and rail traffic. Advanced construction techniques such as prefabrication and modular construction are used to minimize on-site work and reduce construction time. The construction of new stations involves the use of high-quality materials and modern design principles to create comfortable and efficient passenger facilities. The stations are equipped with advanced ticketing systems, passenger information displays, and security systems to enhance the passenger experience. The integration of green spaces and public art also contributes to the aesthetic appeal of the stations. The Stad Ship Tunnel in Norway is an ambitious maritime infrastructure project designed to improve navigational safety and efficiency along the Norwegian coast. The tunnel, measuring 1.1 mile in length, will allow ships to bypass the hazardous Stad Peninsula, known for its treacherous waters and frequent storms. The construction involves excavating through solid rock, requiring advanced drilling and blasting techniques. One of the primary challenges is managing the removal and disposal of the excavated material, which is addressed through a combination of conveyor systems and specialized transport vehicles. The tunnel's design includes a wide and tall cross-section to accommodate large vessels, with reinforced concrete lining to ensure structural integrity. Advanced engineering techniques, such as the use of waterproofing membranes and drainage systems, are employed to manage groundwater and prevent seepage. The project also incorporates state-of-the-art navigation and safety systems, including automated traffic management and emergency response facilities. Once completed, the Stad Ship Tunnel will significantly enhance maritime safety, reduce travel time, and promote economic development by providing a reliable and efficient passage for shipping along Norway's coast. The tunnel is expected to become a major attraction, drawing tourists and boosting local economies. The project exemplifies Norway's innovative approach to solving transportation challenges and improving maritime infrastructure. The tunnel will also reduce the environmental impact of shipping by providing a safer and more direct route, minimizing the risk of accidents and spills. Additionally, the project will create job opportunities during the construction phase and beyond, contributing to the economic growth of the region. The construction process employs specialized tunneling equipment, including tunnel boring machines, rock drilling rigs, and high-capacity conveyor systems to manage the excavation and transport of materials efficiently. Let's investigate a massive nuclear plant megaproject next, called Olkiluoto Nuclear Plant Unit 3. Launched with the aim of significantly bolstering Finland's energy independence and reducing carbon emissions, the project has taken on monumental proportions in both scope and budget. Construction of Olkiluoto 3 began in 2005, with the initial goal of completion by 2009. However, a series of technical challenges, regulatory hurdles, and construction delays pushed its anticipated operational start to 2023. The reactor is of the European pressurized reactor type, which is among the most advanced and safest nuclear reactor designs available, incorporating a multitude of redundant safety systems and modern technology to enhance its operational efficiency and safety. This unit alone adds about 1,600 megawatts of capacity to Finland's power grid, enough to power roughly 1.3 million homes. The technical complexities of building a reactor of this sophistication have necessitated innovations in construction methods, including the use of massive concrete pours that ensure the reactor's durability and resistance to any external shocks. One of the notable features of the Olkiluoto 3 project is its containment building, designed to withstand extreme external events like aircraft impacts and natural disasters, setting a new standard in nuclear safety. The volume of concrete and steel used in this project is staggering, with the containment building alone using steel reinforcement that could stretch from Helsinki to Stockholm if laid end to end. Financially, Olkiluoto 3 has been a behemoth, with costs escalating to an estimated $12 billion. This figure places it among the most expensive energy projects in the world, not just for its sheer scale, but also for the complexity and pioneering technology it embodies. Each delay in the timeline not only added to the cost, but also served as a lesson in international engineering projects' complexity, especially in an industry as regulated and safety-focused as nuclear power. Gare du Nord expansion in France is an extensive project aimed at modernizing and expanding one of Europe's busiest railway stations. The expansion involves the construction of new platforms, the renovation of existing facilities, and the creation of additional passenger amenities. The project is designed to accommodate the growing number of passengers and improve the overall efficiency of the station. The construction process for the Gare du Nord expansion begins with site preparation and the demolition of existing structures to make way for the new platforms. This is followed by the excavation of the new platform areas and the installation of deep foundations to support the station's expanded structure. The use of advanced excavation techniques, such as diaphragm walls and secant piles, ensures the stability of the surrounding soil and minimizes the risk of settlement. The new platforms are constructed using reinforced concrete and steel beams, providing a strong and durable foundation for the station's operations. The platforms are designed to accommodate high-speed trains, with precise alignment and level surfaces to ensure smooth boarding and disembarking. The construction process also involves the installation of advanced signaling and communication systems to manage train movements and ensure passenger safety. The renovation of existing facilities includes the upgrading of waiting areas, ticketing offices, and retail spaces. High-quality finishes and modern amenities are specified to enhance the passenger experience. The station's historical architecture is preserved and integrated with the new construction, creating a seamless blend of old and new. The Challange Bridge in India is an engineering marvel, set to be the world's highest railway bridge upon completion. Spanning the Chenab River in the Himalayas, this bridge is part of the Udhampur-Srinagar-Baramulla rail link project, aiming to improve connectivity in the region. The bridge's arch design, stretching 1,315 feet across and rising 1,178 feet above the river, is a testament to advanced engineering and construction techniques. The construction involves the use of high-strength steel to withstand the challenging weather conditions and seismic activity in the region. One of the primary challenges is the erection of the massive arch, which is being done using a combination of cantilever and cable crane methods. Extensive wind tunnel testing and seismic analysis have been conducted to ensure the bridge's stability and safety. The project also includes the construction of approach roads, tunnels, and viaducts to connect the bridge to the existing rail network. Advanced construction methods, such as incremental launching and balanced cantilever construction, are employed to ensure precision and efficiency. The bridge is designed with multiple safety features, including automated monitoring systems to detect structural stresses and movements. Once completed, the Chenab Bridge will significantly reduce travel time, enhance trade and tourism, and provide a crucial link for the Indian railways in this remote and strategic region. The project also promises to boost the local economy by improving accessibility and creating jobs during the construction phase. The bridge will stand as a symbol of modern engineering prowess, attracting tourists and becoming a landmark in the region. Additionally, the improved rail connectivity is expected to facilitate the movement of goods and people, contributing to the economic development of the surrounding areas. The construction process itself has become a training ground for engineers, offering valuable experience in handling complex projects under challenging conditions. The construction of the Chenab Bridge employs specialized machinery such as cable cranes, hydraulic jacks, and high-precision surveying equipment to ensure accurate assembly and alignment of the bridge components. We have to talk about a massive pipeline project that crosses multiple European countries. The Trans-Adriatic Pipeline represents a groundbreaking stride in European energy infrastructure, stretching 878 kilometers from the Greek-Turkish border through Albania and into Italy. Completed in 2020, the pipeline is a key segment of the Southern Gas Corridor, a strategic initiative to reduce dependence on Russian gas by bringing new sources to European markets. The project taps into the vast gas fields of Azerbaijan, specifically the SaintDenis field, which holds an estimated 1.2 trillion cubic meters of gas. Constructing the pipeline was a feat of engineering and environmental planning. The pipeline crosses diverse terrains and climates, from the plains of Greece to the rugged mountains of Albania and the depths of the Adriatic Sea. Each segment poses unique challenges, such as in Albania, where the pipeline ascends to an altitude of over 2,100 meters before descending to sea level, a feat akin to laying a pipeline across the height of Mount Kilimanjaro. The project navigated delicate ecosystems and densely populated areas with minimal disruption. Advanced horizontal directional drilling was used to install sections of the pipeline beneath sensitive areas, avoiding surface disturbance to habitats and human settlements. This project required an immense investment of $4.8 billion, which is a similar cost compared to the new Berlin-Brandenburg Airport. The pipeline's specialty lies in its operational technology, including state-of-the-art compressor stations in Greece and Albania that are capable of reversing flow, meaning that Europe can either receive or send gas depending on supply and demand dynamics. Tehri Dam in India is one of the largest and most complex dam projects in the country. Located on the Bhagirathi River in Uttarakhand, the dam stands at a height of 853 feet and creates a reservoir with a capacity of 2.6 million acre-feet. The construction of Tehri Dam involves several significant engineering challenges, including the dam's foundation in a seismically active region and the need to manage a large volume of water. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tehri Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,000 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines. The Allianz tunnel projects in India are monumental infrastructure developments aimed at improving year-round connectivity between the Kashmir Valley and Ladakh. The Zojila Tunnel, stretching over 9 miles, is set to be one of the longest and highest altitude road tunnels in the world, providing all-weather access through the Himalayan range. The Zee Tunnel at 4.2 miles serves as a crucial link to the Zojila Tunnel. These projects involve cutting through some of the most challenging terrains, characterized by extreme weather conditions and high seismic activity. Advanced tunnel boring machines and new Austrian tunneling methods are employed to navigate these challenges, ensuring precision and safety. One of the primary challenges is the stabilization of loose rock and soil, which is addressed through ground freezing techniques and the installation of rock bolts and shotcrete. The tunnels are designed with multiple safety features, including emergency exits, ventilation systems, and fire detection and suppression systems. During construction, extensive environmental monitoring is conducted to mitigate impacts on the fragile mountain ecosystem. The projects also involve the construction of access roads, bridges, and support infrastructure to facilitate transportation and logistics. These access routes are critical for transporting materials and workers to the remote construction sites, ensuring timely progress. Once completed, these tunnels will drastically reduce travel time, enhance trade and tourism, and improve the strategic mobility of the Indian Armed Forces in this remote region. The projects will also provide significant socio-economic benefits to the local communities, improving access to essential services and boosting economic activities. Enhanced connectivity will foster regional development and integration, making it easier for people and goods to move between these historically isolated areas. Additionally, the tunnels will improve safety and reliability for travelers, reducing the risk of accidents and road closures due to adverse weather conditions. The construction of these tunnels employs specialized machinery such as rock drilling rigs, ground freezing units, and advanced tunnel lining equipment to ensure structural stability and safety. But how about a barrier megaproject that will protect an entire city? Venice, a city renowned for its unique architecture and intricate waterways, has been facing an existential threat from flooding due to rising sea levels and sinking foundations. In response, Italy embarked on one of the most ambitious and technically complex engineering projects in Europe, the Venice Flood Barrier, officially known as the MOST project. Initiated in 2003, the project comprises a series of 78 mobile underwater gates designed to temporarily isolate the Venetian lagoon from the Adriatic Sea during high tides. Spanning 3 inlets that connect the lagoon to the sea, each gate measures 20 meters wide and weighs up to 300 tons. When not in use, these gates rest in caissons on the seafloor filled with water. During high tides, air is pumped into these caissons, causing the gates to rise and block the incoming water. The technical challenges of constructing such a system were immense. Engineers had to develop new materials and methods to ensure the gates could withstand the harsh marine environment, including building special corrosion-resistant barriers that could endure for decades. The project also involved massive dredging operations to lay the foundations of the gates, moving millions of cubic meters of seabed. But besides those challenges, delays and cost overruns were frequent as well, pushing the project's completion date several times. The initial budget ballooned from an estimated $1.6 billion to an eventual total of $5.7 billion, making it one of the most expensive megaprojects in Europe. Unlike conventional dams or levees, the Venice Flood Barrier is designed to be both invisible and temporary, appearing only when needed to protect the historic city. Kosh Tepe Canal in Afghanistan is a massive infrastructure project designed to divert water from the Amu Darya River to irrigate farmland in northern Afghanistan. The canal is expected to be over 150 miles long and will significantly impact the region's agriculture and economy. The construction of the Kosh Tepe Canal involves several engineering challenges, including working in a remote and arid environment with limited infrastructure. The construction process begins with extensive surveying and land acquisition to establish the canal's route. This is followed by large-scale excavation work, which involves the use of heavy machinery such as bulldozers, excavators, and dump trucks to remove vast quantities of earth and rock. The canal's design includes reinforced concrete linings to prevent erosion and seepage, ensuring that water is efficiently transported to the intended agricultural areas. In addition to the main canal, the project includes the construction of numerous secondary canals and distribution channels to deliver water to individual farms and fields. These secondary canals are carefully designed to maximize water distribution efficiency and minimize losses due to evaporation and seepage. The construction of the canal also involves the installation of gates and control structures to manage water flow and distribution. The engineering challenges of the Kosh Tepe Canal project include dealing with harsh environmental conditions, such as extreme temperatures and arid landscapes. Construction crews must work in difficult conditions, often facing temperatures exceeding 100 degrees Fahrenheit. Additionally, the remote location of the project requires the establishment of temporary construction camps and logistical support to provide essential services to the workers. Advanced surveying and mapping technologies are used to plan the canal's route and ensure precise alignment and gradient. This ensures that water flows smoothly through the canal and reaches the intended areas without excessive energy loss. The use of GPS and drone technology allows engineers to monitor progress and make real-time adjustments to the construction process. The Intuit Dome is a state-of-the-art sports and entertainment arena currently under construction in Los Angeles, set to be the new home for the Los Angeles Clippers NBA team. This $1.8 billion project features a futuristic design with a seating capacity of 18,000, providing fans with an unparalleled viewing experience. The construction incorporates advanced engineering techniques, such as a cantilevered steel roof structure that eliminates the need for interior columns, ensuring unobstructed views from every seat. The arena is equipped with cutting-edge technology, including a high-definition scoreboard that wraps around the entire arena and an advanced sound system for an immersive audio experience. One of the major challenges is the integration of sustainable building practices. The Intuit Dome aims to be a net-zero energy building, utilizing a combination of solar panels, energy-efficient systems, and innovative water conservation methods. The project also includes the construction of a multi-story parking structure and extensive landscaping with native plants to create a welcoming environment for fans. Advanced construction methods, such as prefabrication and modular assembly, are used to streamline the building process and reduce construction time. The arena will also feature numerous amenities, including luxury suites, a training facility, and spaces for community events. Once completed, the Intuit Dome will not only serve as a premier sports venue, but also as a catalyst for economic development in the surrounding area, creating jobs and attracting visitors to Los Angeles. The project underscores the importance of integrating modern design with sustainability, setting a new standard for future sports facilities worldwide. The Intuit Dome is poised to become a landmark in Los Angeles, drawing millions of visitors annually and significantly boosting the local economy through tourism and event hosting. The project also includes significant community engagement initiatives, ensuring that the benefits of the new arena extend to the local population through improved infrastructure and social programs. The construction utilizes advanced machinery, including mobile cranes, steel erection rigs, and prefabrication technology, to ensure precise and efficient assembly of the structure. It's time to move over to Switzerland for an incredibly expansive collider project. The Large Hadron Collider, straddling the Swiss-French border near Geneva, represents one of the most audacious experiments in the history of science. With a project cost of $4.75 billion, this behemoth is not only the world's largest particle accelerator, but also a centerpiece in our quest to unravel the mysteries of the universe. Envision a circular tunnel 27 kilometers in circumference, buried up to 175 meters underground. This isn't just any tunnel, it's a superhighway where protons travel at nearly the speed of light, colliding 600 million times per second. These collisions generate temperatures a million times hotter than the center of the sun, momentarily recreating the conditions of the universe a fraction of a second after the Big Bang. The project's construction required the precision of aligning its two beams to within a hair's breadth over its 27-kilometer length. The magnets used to steer the beams are superconducting and must be cooled to -271.3 degrees Celsius. In 2012, the collider proved its worth by confirming the existence of the Higgs boson, often called the God particle. This elusive particle, key to the theory that explains how other particles get their mass, had remained only a theory for nearly 50 years until the collider's experiments confirmed it. But the Large Hadron Collider isn't just about particle physics. It's a hub of innovation that's propelled advances in fields like medical imaging and computing. For instance, technologies developed at CERN have led to improvements in PET scans, a crucial medical diagnostic tool. Tarbela Dam in Pakistan is one of the largest earth-filled dams in the world, located on the Indus River. The dam stands at a height of 485 feet and creates a reservoir with a capacity of 11.62 million acre-feet. The construction of Tarbela Dam involved several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tarbela Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 478 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines. The Xinjiang Solar Power Plant in China is one of the world's largest solar farms, covering over 30 square miles in the Gobi Desert. This massive renewable energy project is set to generate 2 gigawatts of electricity, enough to power around 1.5 million homes annually. The construction of the plant involves the installation of millions of photovoltaic panels, mounted on advanced tracking systems that follow the sun's path to maximize energy capture. Engineers have designed these systems to withstand the harsh desert environment, including extreme temperatures and high winds. One of the key challenges in this project is the logistics of transporting and installing such a vast number of solar panels and supporting structures in a remote location. To address this, the project employs a modular construction approach, allowing for efficient assembly and scalability. Additionally, innovative dust mitigation techniques are implemented to maintain panel efficiency, such as using anti-dust coatings and robotic cleaning systems. The plant is connected to the grid via high-voltage direct current transmission lines, which are capable of transmitting electricity over long distances with minimal losses. The project also incorporates energy storage solutions to ensure a stable supply of electricity, even during periods of low solar irradiance. These energy storage systems are crucial for balancing supply and demand, enhancing grid stability. This solar power plant represents a significant step towards reducing carbon emissions and promoting sustainable energy development in China. By harnessing the vast solar potential of the Gobi Desert, the project not only contributes to China's renewable energy targets, but also sets a benchmark for large-scale solar energy projects worldwide. The plant's success could pave the way for similar projects in other desert regions across the globe, demonstrating the viability of solar power as a major energy source. The project will also stimulate economic development in the region by creating jobs and providing a reliable energy source for local industries. For the next project, it's time to move over to Belgium. The LNG terminal Zeebrugge is strategically positioned at the crossroads of maritime routes that link northern Europe with LNG-producing regions, including Qatar and the United States. The facility serves as a critical reception point for liquefied natural gas, which is then regasified and fed into the European gas grid. This project, initiated with an eye on the future energy landscape, features state-of-the-art technology, including LNG storage tanks and regasification units. These tanks are massive, each with a capacity to store up to 180,000 cubic meters of LNG, roughly equivalent to 72 Olympic-sized swimming pools per tank. The terminal's regasification capability stands at an impressive rate, able to process billions of cubic meters of gas annually, directly feeding into Europe's energy network. The completion of the terminal is set for 2026, aiming to address one of Europe's most pressing problems: energy dependency. By increasing the number of entry points for LNG into Europe, the terminal not only diversifies the energy supply, but also stabilizes it, making it less susceptible to geopolitical fluctuations that can affect natural gas pipelines from traditional sources. With a total investment of $1.2 billion, this project aligns with the likes of the Fehmarn Belt fixed link between Denmark and Germany. The specialty of the Zeebrugge project isn't just in its operational capabilities, but also in its design and environmental considerations. Featuring advanced vapor recovery systems, the terminal minimizes environmental impact by capturing and reliquefying gas that evaporates during operations, showcasing a commitment to sustainable practices in industrial design. Varso Dam in the United States is being expanded to nearly double its current capacity, making it one of the largest dam expansion projects in the country. The project involves raising the dam height by 131 feet, which will increase the reservoir's capacity from 42,000 acre-feet to 119 acre-feet. This expansion requires significant engineering and construction efforts, including the use of roller-compacted concrete to construct the new dam structure. The construction process begins with extensive site preparation, including the excavation of the existing dam and the construction of temporary diversion tunnels to redirect water flow. The diversion tunnels are critical to maintaining river flow and minimizing the impact on downstream ecosystems during construction. Once the site is prepared, the foundation is laid using high-strength concrete to ensure stability and durability. RCC is a type of concrete that is placed and compacted using earth-moving equipment, allowing for the rapid construction of large-scale concrete structures. The RCC is placed in layers, which are then compacted using vibratory rollers to ensure maximum density and strength. This method is highly efficient and allows for faster construction times compared to traditional concrete pouring methods. The use of RCC also reduces the amount of formwork required, as the concrete is placed in large quantities and compacted in place. This reduces the need for extensive scaffolding and supports, further speeding up the construction process. The construction of the new spillways and outlet works is also a critical component of the project, ensuring the safety and stability of the dam. The spillways are designed to handle extreme flood events, while the outlet works control the release of water for downstream use. The project also includes the installation of advanced monitoring systems to ensure the dam's safety and performance. These systems include sensors and instruments that monitor the dam's structural integrity, water levels, and environmental conditions in real time. The data collected is used to make informed decisions about dam operations and maintenance. The Cameron LNG project in the United States is a major liquefied natural gas export facility located in Hackberry, Louisiana. This $10 billion project involves the construction of 3 liquefaction trains, each capable of producing 4 million tons of liquefied natural gas per year. The construction includes the installation of advanced liquefied natural gas processing equipment, storage tanks, and extensive pipeline infrastructure to transport natural gas to the facility. One of the primary challenges is ensuring the safety and efficiency of the liquefaction process, which involves cooling natural gas to -260 degrees Fahrenheit. Advanced cryogenic technologies and safety systems are employed to manage the extreme temperatures and pressures involved. The project also includes the construction of a marine terminal with loading facilities to accommodate liquefied natural gas carriers. Extensive environmental assessments and mitigation measures are implemented to minimize the impact on local ecosystems and communities. Once completed, the Cameron Liquefied Natural Gas Project will significantly increase the United States liquefied natural gas export capacity, contributing to global energy security and economic growth. The project is expected to generate substantial economic benefits, including job creation and increased investments in the local economy. The Cameron Liquefied Natural Gas Project highlights the United States' growing role as a major exporter of liquefied natural gas and its contribution to global energy markets. The construction process employs specialized machinery such as cryogenic storage tank fabrication units, high-capacity pipeline construction equipment, and advanced safety monitoring systems to ensure the safe and efficient development of the liquefied natural gas facility. But how about one of the most impressive underground rail projects in Europe? The Jubilee Line extension initiated in the mid-1990s and opened in phases between 1999 and 2000. This extension added 16 kilometers to the Jubilee Line, stretching from Green Park to Stratford and including 11 new stations. This project tackled the acute need for improved transit solutions in underserved areas of East London and supported the regeneration of numerous boroughs along its route. Each station is uniquely designed, with Canary Wharf Station being one of the largest and most impressive, enclosed in a vast glass dome and supporting a daily footfall in the hundreds of thousands. The extension was not just about adding track. It involved sophisticated engineering challenges, particularly in constructing deep-level tunnels beneath some of the most densely developed parts of the city. A workforce of over 3,000 people was engaged, with a peak of 2,000 workers underground during the height of construction. The logistics of moving such numbers in and out of confined spaces safely and efficiently was a testament to the meticulous planning and execution of the project managers. One of the most notable features of the Jubilee Line extension is its integration of art and architecture within the public transport system. Each new station features works by different artists, making the line a cultural tour as much as a transit route. On the technical front, the extension required laying down enough concrete to fill 30 Olympic-sized swimming pools and enough steel to build 2 Eiffel Towers. The challenges were manifold, including financial overruns and delays that pushed the final cost to $4.3 billion, a figure that reveals the complex nature of urban underground construction. Philadelphia International Airport in the United States is undergoing a significant expansion and modernization project to enhance its capacity and facilities. The project includes the construction of a new terminal, the expansion of existing terminals, and improvements to the airport's runways and taxiways. The construction process involves extensive use of precast concrete and steel structures to ensure rapid and efficient assembly. The new terminal's construction begins with site preparation, which includes clearing and grading the site and installing deep foundations to support the terminal structure. Precast concrete panels and steel beams are then assembled to form the terminal's framework, followed by the installation of roofing and cladding systems. The use of precast concrete allows for high precision in manufacturing, reducing the likelihood of errors during assembly and speeding up the construction process. The expansion of existing terminals involves complex engineering work to integrate new structures with the old ones seamlessly. This requires careful planning and execution to avoid disruptions to airport operations. Advanced construction techniques, such as modular construction and prefabrication, are used to minimize on-site work and reduce construction time. The project also includes significant improvements to the airport's runways and taxiways. This involves the construction of new taxiways and the expansion of existing runways to accommodate larger aircraft. High-precision paving machines are used to ensure the surfaces are smooth and level, which is critical for safe aircraft operations. Additionally, advanced lighting and navigation systems are installed to enhance visibility and safety. The Westgate Tunnel project in Melbourne is a significant infrastructure initiative designed to alleviate traffic congestion and improve travel times in one of Australia's busiest urban areas. The $6.7 billion project involves constructing a 4-mile toll road with twin tunnels under Yarraville, a new bridge over the Maribyrnong River, and the widening of the Westgate Freeway. The project is a key component of the broader Victorian government's infrastructure plan to modernize and enhance the city's transport network. The tunnels will be constructed using massive tunnel boring machines, each weighing 4,000 tons and stretching 300 feet long. These tunnel boring machines are designed to excavate through diverse geological conditions, including soft clays and basalt rock, while simultaneously installing precast concrete segments to form the tunnel walls. Managing the disposal of the enormous volumes of excavated material is a key challenge, and this will be transported to designated sites for reuse or environmentally safe disposal. Advanced ventilation and air quality monitoring systems will ensure the safety of workers and the surrounding community. Noise and vibration mitigation measures are crucial to minimize the impact on nearby residents. The new cable-stayed bridge over the Maribyrnong River is designed to accommodate increased traffic volumes and enhance structural resilience against seismic activities. The project's integration of smart traffic management systems aims to optimize traffic flow and reduce congestion. Upon completion, the Westgate Tunnel is expected to significantly cut travel times, reduce congestion on the Westgate Bridge, and provide a much-needed alternative route for Melbourne's commuters and freight transport. The project also promises to enhance Melbourne's transport network by creating new cycling and pedestrian pathways, connecting key parts of the city and contributing to a more sustainable urban environment. Additionally, the construction phase is expected to generate thousands of jobs, providing a significant boost to the local economy. Old Oak Common Station in the United Kingdom is a key component of the High Speed 2 project, envisioned to become a major rail interchange. This station is designed to integrate HS2 with the existing Crossrail and Great Western Main Line, making it a significant node in London's transport network. The construction involves several sophisticated engineering challenges and innovative construction methods. The project primarily utilizes the cut and cover technique for constructing the underground sections. This method begins with the excavation of a large trench, which is then lined with concrete to form the walls and base of the station. The structure is built within this trench before it is covered over again. This approach minimizes the impact on the surrounding urban environment and reduces the need for extensive tunneling. The excavation alone is a massive undertaking requiring the removal of thousands of cubic meters of earth, which is then transported away from the site. Construction at Old Oak Common involves significant use of prefabricated elements and modular construction techniques. Prefabrication allows various components of the station, such as platform sections, staircases, and wall panels, to be manufactured off-site in controlled conditions. These components are then transported to the site and assembled, which improves quality control and speeds up the construction process. Modular construction further enhances efficiency by allowing large sections of the structure to be built simultaneously rather than sequentially. One of the critical challenges in the construction of Old Oak Common is integrating the new station with the existing rail infrastructure without causing significant disruptions. This requires meticulous planning and coordination. Advanced scheduling software and building information modeling are employed to simulate construction sequences and optimize workflows. BIM is particularly valuable as it allows engineers to create detailed 3D models of the station and its components, facilitating clash detection and ensuring all elements fit together perfectly. In addition to the structural aspects, the construction of Old Oak Common also involves extensive work on the rail systems. This includes laying new tracks, installing signaling systems, and integrating with the existing rail network. High-precision track laying machines are used to ensure the tracks are positioned with millimeter accuracy, essential for the smooth operation of high-speed trains. The station's extensive facilities, including retail spaces, waiting areas, and service facilities, require a substantial amount of interior work. High-quality finishes and fixtures are specified to enhance the passenger experience. The integration of advanced passenger information systems, ticketing machines, and security systems is also a major focus, ensuring the station is equipped to handle high volumes of passengers efficiently and safely. It's time to travel to Germany, where the Rastatt Tunnel is located. This underground endeavor aims to improve the European rail network, specifically designed to alleviate the strain on existing rail routes and significantly enhance cargo and passenger travel efficiency between Karlsruhe and Basel. The Rastatt Tunnel stretches over a length of 4,270 meters, and it will end up costing around $1.2 billion. Construction kicked off in 2016, but it hasn't been without its challenges. In 2017, a significant setback occurred when part of the tunnel collapsed, causing extensive delays and requiring a reevaluation of project strategies and safety measures. Approximately 2,000 workers have been involved in this mega project, utilizing state-of-the-art construction methods such as tunnel boring machines that carve through the earth with precision. The tunnel features twin tubes, each 10 meters in diameter, which is about as wide as 3 cars parked side by side. These massive tubes are designed to handle the increased rail traffic, with an expected completion and operational date set for 2026. Material-wise, the project is a showcase of modern engineering, using thousands of tons of steel and concrete to ensure structural integrity and safety. In terms of problem solving, the tunnel is a crucial component in the larger strategy to create a more cohesive and efficient European transit network. But what about the most expensive megaproject located in Europe? High Speed 2 is poised to be one of the most transformative rail projects in European history, designed to connect London with the north of England and potentially the central belt of Scotland. The project's primary objective is to enhance connectivity, reduce travel times between major cities, and alleviate congestion on the UK's existing rail network. Initiated with the intention to drastically reduce travel times, HS2 will see trains operating at speeds of up to 250 miles per hour. Upon its anticipated completion, the journey from London to Birmingham will be cut to just 45 minutes, compared to the current duration of 1 hour and 20 minutes. The project will lay down hundreds of miles of track, which requires the excavation and movement of millions of tons of earth. The project's scale is mirrored by its workforce requirements, with tens of thousands of jobs expected to be created during construction. Additionally, HS2 is a catalyst for technology and innovation in construction, employing advanced techniques in tunneling, bridging, and environmental conservation. The trains are planned to be powered by zero-carbon energy from day one of operations, aligning with the UK's broader environmental goals. The new rail lines themselves are designed to integrate with the natural landscape, incorporating green tunnels and wildlife crossings to minimize the environmental impact. However, HS2 has faced considerable problems and controversies, particularly regarding its cost and the environmental impact of its construction. With its budget now revised to an estimated $130 billion, HS2 ranks as the most expensive infrastructure project undertaken in Europe. This investment underscores the UK government's commitment to revolutionizing transport, but has also sparked debates on fiscal responsibility and environmental stewardship. Despite these challenges, the potential benefits of HS2 are substantial. It is expected to double the number of seats available out of London Euston, reducing road congestion. Etihad Rail in the United Arab Emirates is a major infrastructure project aimed at creating a national railway network to connect the country's key cities and industrial centers. The project involves the construction of new railway tracks, the creation of new stations, and the integration of advanced signaling and communication systems. The construction process involves several significant engineering challenges, including working in a desert environment and integrating with existing transport infrastructure. The construction process begins with extensive site preparation, including the clearing and grading of the site and the installation of deep foundations to support the new railway tracks. The tracks are constructed using high-quality steel rails and reinforced concrete sleepers, which provide durability and stability. The construction process also involves the installation of advanced signaling and communication systems to manage train movements and ensure passenger safety. The construction of new stations involves the use of high-quality materials and modern design principles to create comfortable and efficient passenger facilities. The stations are equipped with advanced ticketing systems, passenger information displays, and security systems to enhance the passenger experience. The integration of green spaces and public art also contributes to the aesthetic appeal of the stations. The project also includes the construction of maintenance depots and freight terminals to support the operation of the railway network. These facilities are equipped with advanced machinery and equipment to ensure the efficient maintenance and operation of the trains. The construction of these facilities involves the use of high-quality materials and modern construction techniques to create durable and efficient structures. The engineering challenges of the Etihad Rail project include dealing with harsh environmental conditions, such as extreme temperatures and sandstorms. Construction crews must work in difficult conditions, often facing temperatures exceeding 120 degrees Fahrenheit. Additionally, the remote location of some sections of the railway requires the establishment of temporary construction camps and logistical support to provide essential services to the workers. Advanced surveying and mapping technologies are used to plan the railway routes and ensure precise alignment and gradient. This ensures that trains can travel at high speeds and reach their destinations efficiently. The use of GPS and drone technology allows engineers to monitor progress and make real-time adjustments to the construction process. The Yangtze River Tunnel in China is an ambitious infrastructure project designed to improve connectivity between the cities of Shanghai and Nantong. This 6.8-mile tunnel, part of the larger Shanghai-Nantong Railway project, is one of the longest underwater tunnels in the world. The construction involves the use of advanced tunnel boring machines to excavate through challenging geological conditions, including soft soils and high water pressures. One of the primary challenges is ensuring the structural integrity and safety of the tunnel, which is addressed through the use of high-strength, waterproof concrete and advanced reinforcement techniques. The project also includes the installation of state-of-the-art ventilation, lighting, and safety systems to ensure a safe and comfortable environment for passengers. Extensive environmental assessments and mitigation measures are implemented to minimize the impact on the Yangtze River ecosystem. Once completed, the Yangtze River Tunnel will significantly reduce travel time between Shanghai and Nantong, enhancing regional connectivity and economic development. The tunnel is expected to become a major transportation artery, facilitating the movement of people and goods and contributing to the economic growth of the region. Next up, we have to talk about one of the most expensive electrical projects in Europe, called the Viking Link project. This is an ambitious power connection project stretching over 760 kilometers between the United Kingdom and Denmark. Its primary aim is to enhance the security and sustainability of energy supply by enabling the transfer of up to 1,400 megawatts of electricity between the two countries, enough to power approximately 1.4 million homes. Initiated in 2020, this project is pivotal in fostering energy cooperation across borders. The construction involves laying submarine and underground cables from Revsing in Denmark to Bicker Fen in Lincolnshire. These cables are engineered to withstand harsh marine environments and provide a reliable conduit for electricity over decades. The technology used in the Viking Link incorporates high-voltage direct current systems, which are more efficient over long distances than the more common alternating current systems. Addressing challenges such as environmental impact and technical complexities, the project required meticulous planning and consultation with marine biologists to minimize disruption to marine life. Additionally, engineers faced the technical challenge of routing cables through varied terrains, including the North Sea's challenging seabed. The project also incorporates cutting-edge converter stations at each end, which are crucial for converting electricity between DC used in transmission and AC used in domestic power grids. With a total cost of $1.92 billion, this project represents a major investment in sustainable infrastructure. The Doha Solar Park in India is one of the world's largest solar energy projects, designed to generate 5 gigawatts of electricity. located in the Doha Special Investment Region in Gujarat. This solar park covers over 27,000 acres. The project involves the installation of millions of photovoltaic panels, advanced inverters, and extensive transmission infrastructure to connect the generated power to the grid. One of the major challenges is the harsh environmental conditions, including high temperatures and dust, which necessitate the use of durable and efficient solar technologies. To address this, the project employs bifacial solar panels, which can capture sunlight on both sides, and robotic cleaning systems to maintain panel efficiency. The solar park also includes energy storage solutions, such as large-scale battery systems, to ensure a stable supply of electricity. The construction involves a modular approach, allowing for phased development and scalability. Extensive environmental assessments are conducted to minimize impacts on the local ecosystem, including measures to protect wildlife and manage water resources sustainably. The project is designed to integrate seamlessly with the existing grid infrastructure, ensuring reliable power delivery. Once completed, the Doha Solar Park will significantly contribute to India's renewable energy capacity, reducing carbon emissions and promoting sustainable development. The project will also provide a boost to the local economy by creating jobs and fostering the growth of a clean energy industry in the region. By harnessing solar energy, the Doha Solar Park sets a precedent for future renewable energy projects, showcasing India's commitment to sustainable development. The project is expected to attract further investments in renewable energy, positioning India as a global leader in the clean energy sector. The solar park will also serve as a model for large-scale solar energy projects worldwide, demonstrating the potential of renewable energy to meet the growing energy demands sustainably. The construction process utilizes advanced machinery such as solar panel mounting systems, high-capacity cranes, and automated assembly lines to ensure efficient and precise installation of the solar arrays. The Punta Sierra Wind Farm in Chile is an impressive renewable energy project located in the Coquimbo region, near the city of La Higuera. This project is designed to harness the strong and consistent winds of the coastal region to generate electricity. With a total installed capacity of 82 megawatts, the Punta Sierra Wind Farm is capable of producing enough energy to power approximately 60,000 homes. The construction of the wind farm involves several critical components, including the wind turbines, foundations, and the electrical infrastructure needed to connect the farm to the grid. The wind turbines, each with a capacity of 2 megawatts, are manufactured by leading companies in the wind energy sector. These turbines are mounted on towers that are approximately 260 feet tall, allowing them to capture the stronger winds at higher altitudes. The installation of the wind turbines requires meticulous planning and precision engineering. Each turbine consists of multiple components, including the rotor blades, nacelle, and tower sections, which are transported to the site and assembled using large cranes. The foundations for the turbines are constructed using reinforced concrete, designed to support the weight of the turbines and withstand the forces exerted by the wind. In addition to the physical construction, the project also involves the installation of an extensive electrical infrastructure. This includes the construction of a substation and the laying of underground cables to connect the turbines to the substation. The substation is equipped with transformers and switchgear to manage the flow of electricity and ensure a stable connection to the national grid. The Tangier Med Port expansion in Morocco is a major infrastructure project aimed at transforming the port into one of the largest and most modern in Africa. Located on the Strait of Gibraltar, Tangier Med is strategically positioned to serve as a key hub for maritime trade between Europe, Africa, and the Americas. The expansion project includes the construction of new container terminals, logistics zones, and support infrastructure to significantly increase the port's capacity and efficiency. The construction of the new container terminals involves extensive dredging and land reclamation to create additional space for the terminals and berths. The dredging operations are carried out using specialized vessels that remove sediment from the seabed, allowing larger ships to access the port. The reclaimed land is then stabilized and prepared for construction using advanced geotechnical techniques. The new terminals are equipped with state-of-the-art cargo handling equipment, including gantry cranes, automated stacking cranes, and conveyor systems. These facilities are designed to handle the latest generation of ultra-large container ships, significantly increasing the port's throughput capacity. The construction of the terminals involves the installation of heavy-duty concrete foundations and the erection of steel structures to support the cranes and other equipment. In addition to the container terminals, the expansion project includes the development of extensive logistics zones and support infrastructure. These areas are designed to accommodate warehousing, distribution centers, and other logistics services, enhancing the port's role as a regional logistics hub. The construction of these facilities involves earthworks, concrete pouring, and the installation of utility networks to support the operations. One of the significant challenges of the 10-year Medport expansion project is coordinating the construction activities while keeping the existing port operations running smoothly. The construction teams must work closely with port authorities and operators to minimize disruptions and ensure the safety of workers and cargo. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The Dunkirk LNG terminal in France is a critical infrastructure project designed to enhance the country's energy security and diversify its sources of natural gas. Located in the port of Dunkirk, the terminal has a capacity to handle up to 13 billion cubic meters of natural gas per year, making it one of the largest LNG terminals in Europe. The project includes the construction of storage tanks, regasification units, and support infrastructure to import and process liquefied natural gas. The construction of the storage tanks is one of the most complex aspects of the project. Each tank is designed to store LNG at a temperature of -260 degrees Fahrenheit, requiring advanced cryogenic engineering and materials. The tanks are double-walled structures with an inner steel tank surrounded by an outer concrete shell. The space between the two walls is filled with insulation to maintain the low temperature and prevent heat ingress. The regasification units are responsible for converting the LNG back into its gaseous state for distribution through the national gas network. These units consist of heat exchangers and vaporization systems that use seawater or ambient air to warm the LNG. The construction of these units involves the installation of advanced piping systems and control equipment to manage the flow and pressure of the gas. In addition to the storage tanks and regasification units, the project includes the construction of a jetty to accommodate LNG carriers. The jetty is equipped with unloading arms and safety systems to transfer the LNG from the carriers to the storage tanks. The construction of the jetty involves extensive dredging and piling works to create a stable foundation in the marine environment. One of the significant challenges of the Dunkirk LNG terminal project is ensuring the safety and security of the facility. The terminal is equipped with advanced safety systems, including gas detection, fire suppression, and emergency response equipment to protect workers and the surrounding communities. Additionally, the project must adhere to strict environmental regulations to minimize the impact on the marine ecosystem and air quality. Victoria Dockside in Hong Kong is a major mixed-use development project that transforms the Tsim Sha Tsui waterfront into a vibrant hub for business, culture, and tourism. The project includes the construction of office towers, luxury residences, retail spaces, and cultural venues, creating a dynamic urban environment that reflects Hong Kong's status as a global city. The construction of Victoria Dockside involves several key components, including the high-rise buildings, the waterfront promenade, and the public spaces. The high-rise buildings are designed by leading architects and feature state-of-the-art engineering and construction techniques. The towers are constructed using reinforced concrete and steel, with advanced facade systems to enhance energy efficiency and aesthetic appeal. The waterfront promenade is a central feature of the development, providing a scenic and accessible space for residents and visitors. The construction of the promenade involves extensive landscaping, paving, and the installation of amenities such as seating, lighting, and public art. The design incorporates sustainable elements, such as green roofs and rainwater harvesting systems, to enhance environmental performance. In addition to the built structures, Victoria Dockside includes the development of public spaces and cultural venues. These spaces are designed to foster community engagement and cultural exchange, with features such as open plazas, performance stages, and art installations. The construction of these spaces involves careful planning and coordination to integrate them seamlessly with the surrounding urban fabric. One of the significant challenges of the Victoria Dockside project is managing construction activities in a densely populated urban environment. The construction teams must work closely with local authorities and stakeholders to minimize disruptions and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the waterfront and the surrounding communities. Malacca Gateway in Malaysia is an ambitious waterfront development project aimed at transforming the historic city of Malacca into a major tourism and commercial hub. The project includes the construction of a series of man-made islands, luxury hotels, shopping malls, and entertainment venues, creating a vibrant destination that attracts visitors from around the world. The construction of Malacca Gateway involves several critical components, including land reclamation, the construction of infrastructure, and the development of tourism and commercial facilities. The land reclamation process involves dredging and filling the seabed to create the new islands, requiring advanced geotechnical engineering and environmental management. The reclaimed land is stabilized and prepared for construction using techniques such as soil compaction and reinforcement. The development of infrastructure includes the construction of roads, bridges, and utility networks to support the new islands. These elements are designed to provide seamless connectivity and ensure the efficient operation of the development. The construction of roads and bridges involves extensive earthworks, concrete pouring, and steel reinforcement to create durable and reliable structures. In addition to the infrastructure, Malacca Gateway includes the development of luxury hotels, shopping malls, and entertainment venues. These facilities are designed by leading architects and feature state-of-the-art construction techniques and materials. The construction of these buildings involves advanced formwork, steel erection, and facade systems to create visually striking and functional spaces. One of the significant challenges of the Malacca Gateway project is managing the environmental impact of the development. The project includes extensive environmental assessments and mitigation measures to protect the marine ecosystem and preserve the natural beauty of the area. Additionally, the construction teams must work closely with local communities and stakeholders to address concerns and ensure the sustainable development of the project. The Eurasia Tunnel in Turkey is a major infrastructure project that significantly improves connectivity between the European and Asian sides of Istanbul. The tunnel, which runs beneath the Bosphorus Strait, provides a vital link for both passenger and freight traffic, reducing travel time and easing congestion on the city's bridges. The tunnel is approximately 3.4 miles long, with a two-deck design to accommodate both cars and light vehicles. The construction of the Eurasia Tunnel involves several critical components, including the tunnel boring machine, the tunnel lining, and the ventilation and safety systems. The TBM is a specialized piece of equipment that excavates and installs the tunnel segments simultaneously. The machine is designed to operate in the challenging geological conditions beneath the Bosphorus, using advanced cutting and reinforcement techniques to ensure the stability and safety of the tunnel. The tunnel lining is constructed using precast concrete segments, which are assembled as the TBM advances. These segments are designed to provide structural support and prevent water ingress, ensuring the durability and longevity of the tunnel. The lining also includes features such as fire-resistant materials and drainage systems to enhance safety and performance. In addition to the physical construction, the Eurasia Tunnel includes the installation of advanced ventilation and safety systems. These systems are designed to manage air quality and provide emergency response capabilities in the event of an incident. The ventilation system includes fans and ductwork to circulate fresh air and remove exhaust gases, while the safety systems include fire detection and suppression equipment, emergency lighting, and communication networks. One of the significant challenges of the Eurasia Tunnel project is managing the construction activities beneath a busy and densely populated city. The construction teams must use advanced monitoring and control techniques to minimize disruption and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The Riyadh Metro in Saudi Arabia is an ambitious urban rail project designed to transform public transportation in the capital city. The metro system comprises 6 lines, spanning a total of 110 miles and including 85 stations. The construction of the Riyadh Metro involves advanced tunneling techniques, station construction, and the installation of state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large, cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger comfort and safety. The train control systems for the Riyadh Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The auto system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Riyadh Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Riyadh, particularly the high temperatures, require special considerations for worker safety and construction materials. The Long Than International Airport in Vietnam is a major infrastructure project aimed at enhancing the country's aviation capacity and supporting economic growth. Located in Dong Nai Province near Ho Chi Minh City, the airport is designed to handle up to 100 million passengers and 5 million tons of cargo annually. The project includes the construction of a new terminal, runways, and support infrastructure. The construction of the new terminal involves extensive earthworks, concrete pouring, and steel erection. The terminal is designed with a modern, open layout, featuring large glass windows and high ceilings to create a spacious and welcoming environment. Advanced construction techniques, such as prefabrication and modular construction, are used to speed up the building process and ensure high-quality finishes. The runways are designed to accommodate the largest commercial aircraft, requiring precise engineering to ensure smooth and safe landings and takeoffs. The construction of the runways involves extensive earthworks, grading, and paving, using advanced materials and techniques to create a durable and reliable surface. In addition to the terminal and runways, the project includes the construction of support infrastructure, such as taxiways, aprons, and utility networks. These elements are designed to provide seamless connectivity and ensure the efficient operation of the airport. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of the Long Than International Airport project is managing construction activities while minimizing disruptions to existing airport operations and the surrounding communities. Engineers and planners must carefully coordinate construction schedules and activities to ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the environment and ensure compliance with international standards. The DigIndy Dam in the Democratic Republic of the Congo is an ambitious hydroelectric project designed to harness the power of the Congo River and provide electricity to millions of people across Africa. Once completed, the dam is expected to have a generating capacity of up to 40,000 megawatts, making it the largest hydroelectric project in the world. The project includes the construction of a series of dams, powerhouses, and transmission lines. The construction of the dams involves extensive earthworks, concrete pouring, and steel reinforcement to create stable and durable structures. The main dam is designed to span the Congo River, creating a large reservoir to store water for power generation. The construction process includes the diversion of the river, the excavation of foundations, and the erection of concrete and steel structures to form the dam. The powerhouses are equipped with turbines and generators that convert the energy of the flowing water into electricity. The construction of the powerhouses involves the installation of advanced mechanical and electrical systems, requiring precision engineering and expertise. The turbines are designed to operate efficiently under varying water flow conditions, ensuring a reliable and continuous supply of electricity. In addition to the dams and powerhouses, the project includes the construction of transmission lines to distribute the electricity generated by the dam. These lines are designed to transport high-voltage electricity over long distances, connecting the dam to major cities and industrial centers across Africa. The construction of the transmission lines involves the erection of steel towers, the stringing of conductors, and the installation of substations to manage the flow of electricity. One of the significant challenges of the DigIndy Dam project is managing the environmental and social impacts. The construction and operation of the dam affect the local ecosystem and communities. necessitating extensive environmental assessments and mitigation measures. Engineers and planners work closely with environmental experts and local communities to address concerns and ensure sustainable development. The Auckland City Rail Link in New Zealand is a major infrastructure project designed to enhance public transportation and improve connectivity in the city. The project involves the construction of a new underground rail line, spanning approximately 3.5 kilometers and including several new stations. The rail link is expected to significantly reduce travel times and increase the capacity of Auckland's rail network. The construction of the Auckland City Rail Link involves several critical components, including tunneling, station construction, and the installation of rail infrastructure. Tunneling is carried out using tunnel boring machines, which excavate and install tunnel segments simultaneously. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The use of TBMs allows for rapid and efficient tunneling, minimizing disruption to the surface and surrounding areas. The construction of the new stations involves extensive excavation, concrete pouring, and steel reinforcement. Each station is designed with multiple levels, including concourses, platforms, and service areas. The stations are equipped with modern amenities and safety systems, ensuring a comfortable and secure environment for passengers. The construction process requires careful coordination to integrate the new stations with existing rail and urban infrastructure. In addition to the physical construction, the Auckland City Rail Link includes the installation of advanced rail infrastructure, such as tracks, signaling systems, and power supply. The tracks are constructed using continuous welded rail, providing a smooth and reliable surface for trains. The signaling systems are designed to manage train movements and ensure safety, while the power supply includes the installation of overhead lines and substations to provide electricity to the trains. One of the significant challenges of the Auckland City Rail Link project is managing construction activities in a busy urban environment. Engineers and planners must carefully coordinate construction schedules and activities to minimize disruptions to traffic, businesses, and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the urban environment and ensure the safety of workers and the public. The Maputo-Caetano Bridge in Mozambique is a major infrastructure project that significantly improves connectivity between the capital city of Maputo and the southern region of Caetano. The bridge spans approximately 1.6 kilometers across the Maputo Bay, making it the longest suspension bridge in Africa. The project includes the construction of access roads, toll plazas, and support infrastructure to facilitate the flow of traffic. The construction of the Maputo-Caetano Bridge involves several critical components, including the main suspension cables, the bridge deck, and the supporting towers. The main cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. These cables are anchored to massive concrete blocks on either side of the bay, providing the necessary stability and strength. The bridge deck is constructed using prefabricated steel sections, which are transported to the site and assembled using large cranes. Each section is carefully lifted into place and connected to the main cables using hangers. The deck is then paved with asphalt and equipped with safety barriers and lighting systems to ensure the safety and comfort of drivers. The supporting towers, which rise to a height of approximately 141 meters, are constructed using reinforced concrete. These towers are designed to withstand the forces exerted by the cables and the traffic load, as well as environmental factors such as wind and earthquakes. The construction of the towers involves extensive formwork, concrete pouring, and steel reinforcement to create a stable and durable structure. One of the significant challenges of the Maputo-Caetano Bridge project is the complex engineering required to construct such a long and high bridge over a deep and wide bay. The construction teams must use advanced surveying and alignment techniques to ensure the bridge is straight and level. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The New York Penn Station expansion in the United States is a major infrastructure project designed to increase the capacity and improve the functionality of one of the busiest transportation hubs in the country. The project includes the construction of new concourses, platforms, and support infrastructure to accommodate growing passenger demand and enhance the overall experience for travelers. The construction of the new concourses involves extensive excavation, concrete pouring, and steel erection to create large, open spaces for passengers. These concourses are designed with modern amenities, including seating areas, retail spaces, and digital displays to provide information and entertainment. The construction process requires careful coordination to integrate the new concourses with the existing station infrastructure and ensure minimal disruption to ongoing operations. The new platforms are designed to accommodate longer and more frequent trains, increasing the station's capacity and efficiency. The construction of these platforms involves the installation of tracks, signaling systems, and safety features to ensure smooth and reliable train movements. The platforms are equipped with modern amenities, such as seating, lighting, and accessibility features to enhance passenger comfort and safety. In addition to the concourses and platforms, the project includes the construction of support infrastructure, such as ventilation systems, electrical networks, and emergency response facilities. These elements are essential for the safe and efficient operation of the station, providing the necessary support for passengers and staff. The construction of this infrastructure involves the installation of advanced systems and equipment to manage air quality, power supply, and safety in the station. The successful completion of the New York Penn Station expansion represents a significant investment in the future of New York's transportation infrastructure. The project enhances the capacity and functionality of the station, improving the overall experience for travelers and supporting the city's economic growth. The Copenhagen Airport expansion in Denmark is a major infrastructure project designed to increase the airport's capacity and improve passenger services. The West Link project is expected to significantly reduce travel times and increase the capacity of Gothenburg's rail network. The construction of the Gothenburg West Link involves several critical components, including tunneling, station construction, and the installation of rail infrastructure. Tunneling is carried out using tunnel boring machines, which excavate and install tunnel segments simultaneously. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The use of TBMs allows for rapid and efficient tunneling, minimizing disruption to the surface and surrounding areas. The construction of the new stations involves extensive excavation, concrete pouring, and steel reinforcement. Each station is designed with multiple levels, including concourses, platforms, and service areas. The stations are equipped with modern amenities and safety systems, ensuring a comfortable and secure environment for passengers. The construction process requires careful coordination to integrate the new stations with existing rail and urban infrastructure. In addition to the physical construction, the Gothenburg West Link includes the installation of advanced rail infrastructure, such as tracks, signaling systems, and power supply. The tracks are constructed using continuous welded rail, providing a smooth and reliable surface for trains. The signaling systems are designed to manage train movements and ensure safety, while the power supply includes the installation of overhead lines and substations to provide electricity to the trains. The Gothenburg West Link represents a significant investment in Sweden's public transportation infrastructure. The project is expected to enhance connectivity, reduce congestion, and support sustainable urban development in Gothenburg, making it a key component of the city's future growth. The Port of Houston is undergoing a significant expansion to accommodate increasing maritime traffic and larger vessels. This project aims to deepen and widen the Houston Ship Channel to 46.5 feet and 530 feet, ensuring the port can handle the next generation of mega ships. The expansion involves extensive dredging operations, requiring sophisticated equipment and precise engineering to navigate the challenging conditions of the channel. The dredged material is being repurposed for various beneficial uses, including the creation of new marshlands and habitat restoration projects, showcasing a commitment to environmental sustainability alongside industrial growth. One of the primary challenges of the expansion is managing the continuous operation of the port while construction is underway. This necessitates careful coordination and staging to minimize disruptions to the daily flow of goods. Engineers employ advanced modeling and simulation tools to plan the dredging activities meticulously, ensuring the stability of the channel's banks and the safety of the ongoing port operations. The use of modern dredgers equipped with GPS technology allows for precise excavation, reducing the risk of over-dredging and ensuring the channel meets the required dimensions. In addition to the dredging, the expansion project includes the construction of new berths and the enhancement of existing ones to accommodate the larger vessels. This involves significant civil engineering work, including the installation of high-capacity cranes and other cargo handling equipment. These upgrades are designed to improve the efficiency of cargo transfer operations, reducing turnaround times for ships and enhancing the port's overall capacity. Another critical aspect of the project is the integration of advanced technology to improve the port's operational efficiency. This includes the implementation of automated systems for cargo tracking and handling, as well as the installation of state-of-the-art security measures to safeguard against potential threats. The expansion is expected to significantly boost the port's throughput capacity, allowing it to handle over 200 million tons of cargo annually, which is vital for supporting the economic growth of the region. Let's move over to the next megaproject, which is Amsterdam Central Station, located in the Netherlands. The station is undergoing a comprehensive renovation to transform it into a modern transport hub capable of handling the increasing passenger traffic. The project involves the complete overhaul of the station's infrastructure, including the addition of new platforms, tracks, and passenger facilities. One of the key challenges is maintaining the station's operations while construction is underway, requiring meticulous planning and execution. The renovation includes the construction of a new underground metro station, which will be integrated with the existing railway network. This involves extensive tunneling work beneath the station, using advanced tunneling machines to minimize disruption to the surface activities. The new metro station will feature state-of-the-art facilities, including automated ticketing systems and real-time passenger information displays, enhancing the overall travel experience. Another significant aspect of the renovation is the restoration of the station's historic facade and interior. This requires a delicate balance between preserving the architectural heritage and incorporating modern amenities. Specialized restoration techniques are employed to repair and preserve the original features, while new materials and technologies are used to enhance the building's functionality and safety. The renovation also includes the expansion of the station's concourse and the creation of new retail and dining spaces, providing passengers with a wide range of amenities. The upgraded station will feature improved accessibility, with new elevators and escalators, as well as dedicated facilities for passengers with reduced mobility. The integration of sustainable design elements, such as energy-efficient lighting and ventilation systems, further underscores the project's commitment to environmental responsibility. The construction process involves several phases, starting with the demolition of outdated structures and the excavation of new tunnels. Advanced excavation techniques are used to ensure the stability of the surrounding buildings and infrastructure. Once the tunnels are excavated, the focus shifts to constructing the new metro station and integrating it with the existing railway network. This involves the installation of tracks, signaling systems, and power supplies, as well as the construction of platforms and passenger facilities. The restoration of the historic facade requires careful planning and execution to preserve the architectural integrity of the building. This involves cleaning and repairing the original brickwork, replacing damaged elements, and applying protective coatings to ensure the longevity of the restored features. Inside the station, modern amenities are seamlessly integrated with the historic interior, creating a blend of old and new that enhances the overall passenger experience. The Guadalajara Subway Line 4 is a major infrastructure project aimed at improving public transportation in the city. The new line will span approximately 13 miles, connecting key areas of the city and significantly reducing travel times for commuters. The construction involves the use of advanced tunneling techniques, including the deployment of tunnel boring machines to excavate the underground sections of the line. One of the challenges of the project is navigating the complex geological conditions of the region, which include varying soil types and underground water sources. To address these challenges, engineers use sophisticated geotechnical analysis and monitoring systems to ensure the stability of the tunnels during excavation. The boring machines are equipped with cutting-edge technology to handle the diverse soil conditions, including pressure-balanced cutting heads and automated guidance systems. In addition to the tunneling work, the project includes the construction of new stations and the installation of modern rail infrastructure. The stations are designed with a focus on passenger convenience and safety, featuring spacious platforms, advanced ticketing systems, and real-time information displays. The new line will also incorporate the latest in rail technology, including automated train control systems and energy-efficient rolling stock. Once the tunnels are excavated, the focus shifts to constructing the stations and installing the rail infrastructure. The stations are built using a combination of traditional construction methods and prefabricated elements, allowing for efficient and timely completion. The installation of the rail infrastructure involves laying tracks, installing signaling systems, and setting up power supplies. Advanced technologies, such as automated train control systems, are integrated to ensure the safety and efficiency of the line. But how about an insanely long pipeline megaproject? The Trans-Saharan Gas Pipeline is an ambitious undertaking aimed at transporting natural gas from Nigeria to Europe via Niger and Algeria. The pipeline will span approximately 65 miles, making it one of the longest pipelines in the world. The construction involves a range of engineering challenges, including the need to traverse harsh desert environments and mountainous terrain. One of the key challenges of the project is ensuring the integrity and safety of the pipeline over such a long distance. This requires the use of advanced materials and construction techniques, including high-strength steel pipes and automated welding systems. The pipeline will also be equipped with state-of-the-art monitoring and control systems to detect and respond to any potential issues, such as leaks or pressure fluctuations. The construction of the pipeline involves extensive trenching and welding operations, with specialized equipment and techniques used to handle the diverse terrain. In the desert regions, engineers must contend with extreme temperatures and shifting sands, which can affect the stability of the pipeline. To address these challenges, the pipeline will be buried at a sufficient depth to protect it from environmental factors and ensure its long-term stability. In addition to the technical challenges, the project also involves significant logistical and coordination efforts, given the need to work across multiple countries and jurisdictions. This requires close collaboration between the governments and stakeholders involved, as well as the implementation of robust project management and risk mitigation strategies. The pipeline's route is carefully planned to minimize environmental impact and avoid sensitive areas. Advanced geospatial technologies, such as satellite imaging and geographic information systems, are used to map the terrain and identify the optimal path for the pipeline. This ensures that the pipeline avoids protected areas, wildlife habitats, and other environmentally sensitive regions. The welding of the pipeline segments is a critical phase of the project, requiring precision and expertise to ensure the integrity of the welds. Automated welding systems are used to achieve consistent and high-quality welds, while rigorous quality control measures are implemented to detect and address any defects. The welded pipeline segments are then coated with protective materials to prevent corrosion and enhance their durability. Let's move on to talk about the Los Angeles River Revitalization Project, which aims to transform the historic waterway into a vibrant public space, addressing both environmental and urban development goals. The project involves the restoration of natural habitats, the creation of recreational areas, and the construction of new infrastructure to manage stormwater and improve water quality. One of the difficulties of the project is balancing the need for flood control with the goal of creating a more natural and accessible river environment. This requires the use of innovative engineering solutions, such as the construction of multi-benefit stormwater management facilities and the installation of permeable surfaces to reduce runoff and improve groundwater recharge. The project also includes the removal of concrete channels in certain sections of the river, allowing for the restoration of natural vegetation and wildlife habitats. This involves extensive excavation and regrading work, as well as the planting of native species to support biodiversity. Advanced modeling and simulation tools are used to design and evaluate the hydrological impacts of these changes, ensuring that flood risks are effectively managed. The restoration process begins with the removal of concrete channels and the excavation of the riverbed. Heavy machinery, such as excavators and bulldozers, is used to remove the concrete and regrade the riverbed to create a more natural profile. This is followed by the planting of native vegetation, including trees, shrubs, and grasses, to restore the natural habitat and support wildlife. The construction of stormwater management facilities is a critical component of the project, designed to capture and treat runoff before it enters the river. These facilities include detention basins, bioswales, and constructed wetlands, which use natural processes to filter and clean the water. Permeable surfaces, such as permeable pavement and green roofs, are also installed to reduce runoff and promote groundwater recharge.